Hello, and welcome to Echoes of the Forgotten Earth. This is a corner of the universe where curiosity is allowed to stretch its legs without a stopwatch running in the background, and where big questions get more than a passing glance. This isn't a place for skimming headlines or racing through bullet points. Here, we try to slow things down just enough that we can actually sit with the strange, beautiful, and sometimes unsettling things the cosmos has been keeping right in front of us all along. Tonight, the idea we're drifting into is one that has lingered quietly in the backdrop of astronomy and science fiction for a long time, but almost never gets the slow, deliberate attention it deserves. It's the suggestion that Earth, the ground you're on right now, the world that feels singular and permanent, might not be especially unique in the way we like to imagine. Not unique in terms of meaning or beauty, but in the sense of being alone. That maybe there have been many Earth-like worlds before, wrapped in oceans and continents and atmosphere, perhaps even home to life, and that most of them didn't make it. It's a strange, slightly disquieting thought, isn't it? We tend to picture our planet as the cosmic lottery winner, the one oasis in a hostile universe where all the right pieces fell into place. But what if reality is more tangled than that? What if Earth isn't one in a billion so much as one of the few survivors in a universe strewn with failed attempts? What if, scattered across light years, there are the cold remains of worlds that tried to do what ours has done and simply couldn't hold on? Before we walk any farther into that territory, I want you to pause and notice exactly where you are right now. Not just your city or your country, but the precise, ordinary little nook of the planet you're inhabiting. Are you inside somewhere, with the faint buzz of electronics and appliances surrounding you? Or are you outside, where you can catch the rush of wind in the trees or the low, constant murmur of distant traffic? Is it daytime where you are, with sunlight pouring through windows or drawing long shadows across the ground? Or is it night, with the sky overhead dark, maybe hiding stars behind clouds, or washed out by the glow of a nearby city? Hold that place in your mind for a moment. The room, the street, the park bench, the patch of ground beneath you. Remember that all of it. The air moving in and out of your lungs, the solid surface under your feet, the familiar gravity holding you here, is bound to this one fragile world. This thin film of rock, water, and gas is the only environment any human has ever truly lived in. Every memory you have, every breath you've ever taken, has happened here. That realization can be grounding, but it can also crack open the door to a very different way of seeing things. When Earth is the only habitable place you've ever personally experienced, it's easy to assume it must be rare by default. We don't have a lived frame of reference for any other planets. We can peer through telescopes, send machines to the outer edges of our own solar system, and detect the dim signatures of planets circling distant suns. But none of that is the same as standing on a different world and inhaling a different sky. That's why the notion of other Earth-like planets feels abstract to most of us. On paper, we know the odds. Thousands of exoplanets already catalogued, likely billions more unfound. The statistics say worlds like ours should be common, but they're so unimaginably far away that they might as well be part of a myth cycle. And when something feels mythical, we tend to flatten it into simple categories. We picture two kinds of planets: cold, lifeless rocks, and rare jewels like Earth. But the deeper we dig into the universe, the more it seems there's a vast, complicated middle ground. Worlds that showed promise. Worlds that maybe got started. Worlds that might even have thrived for a while before they didn't. This is where the idea begins to sharpen. If the conditions needed for life aren't impossibly rare, then life itself may not be either. And if life can arise in more than one place, then it follows that some of those living worlds never made it from simple microbes all the way to sprawling, complex ecosystems. There's no cosmic rule that says once a planet sparks life, it gets to keep it forever. Stars evolve, atmospheres seep into space, temperatures swing, catastrophes happen, And life, adaptable as it is, has limits. When a planet pushes past those limits, its story closes. It becomes one more quiet entry in what we might imagine as the universe's private list of failed experiments. Think about our own solar system for a moment. We already have candidates right next door. Mars seems to have once hosted running water and a thicker blanket of air. Venus may have worn oceans before it was transformed into the hottest surface in our planetary family. Even icy moons like Europa and Enceladus harbor hidden oceans today, hinting that they might once have nurtured life or could still do so out of sight. These weren't born as cold, inert stones with no possibilities. They're almost worlds, planets, and moons that nearly fit the bill, and that's just within the reach of a handful of space probes in a single modest solar system. If we can find several near misses in our own backyard, how many more might be scattered throughout the Milky Way? It's easy to let this line of thinking tip into gloom, but it doesn't have to. There's a different, quieter awe in it. It suggests that life hasn't just appeared once, but may have tried to ignite again and again. That the universe might be threaded with untold stories we'll never hear, civilizations that rose and crumbled, forests and reefs that blossomed, then vanished. Oceans that once carried waves and are now nothing but dry, cracked basins under alien suns. And somewhere in all of that, Earth is still here. Not because it was destined to be, but because a particular stack of conditions happened to pile up in our favor. And up to this point, we've sidestepped the kinds of catastrophes that would have shut everything down. Before we wander too far into distant systems and their quiet, unfinished histories, I want to pull this back to you again for a moment. If you could stand on one of those other worlds, even knowing it's lifeless now, would you? Would you want to walk across a dead shoreline and see what clues remain of what used to be there? Would you want to trace the dried riverbeds of a lost ocean, or cross the cracked crust of a failed greenhouse world? Or would you rather leave those places in the realm of imagination, their stories untold? There isn't a right answer to that. But turning the question over in your mind can help us see our own position on Earth a little more clearly. If you've stayed with Echoes of the Forgotten Earth this far, letting your mind drift into this idea with me, I'm going to ask you for a small favor. If you find value in this slow, careful way of exploring a thought one that doesn't sprint to a conclusion, but lingers in the questions, consider liking this video or subscribing. It's a simple act that helps keep this tiny, quiet space alive so more people can share in these longer, gentler explorations. So here we are, standing on a living world, surrounded by the very real possibility that it's just one survivor among countless lost planets. And the only honest way to start making sense of that possibility is to look outward, beyond the familiar blue dome overhead, toward the places that may once have been alive, and now are not. That is where we're going next. From the surface, Earth feels vast and solid. Our senses are tuned to the local scale. Streets and skylines, forests and fields, clouds and weather. Even the horizon seems enormous until you remember that, next to the size of space itself, it's nothing more than a small curve on a ball, less than 13,000 kilometers across. Step far enough back, and the view shifts. From the moon, our planet hangs as a bright marble set against black. From the outer planets, it shrinks to a faint dot that your fingertip can erase. From interstellar distances, even that dot disappears entirely. Every person you've ever known, every story you've ever heard, every recorded moment in human history collapses into a point too small to pick out from background noise. That vantage point has a way of dissolving the old certainty that we are the unquestioned center of anything. The goal isn't to make us feel small for its own sake, though that can happen, but to remind us that we are part of something vastly larger. And within that wider narrative, Earth may not be the lone protagonist. It could be just one character among uncounted others, each planet given its own short chapter in the unfolding history of the universe. Seen that way, the belief that we're the only world that worked stops feeling like a confident statement and starts feeling more like a bet we currently happen to be winning. For now. Astronomers have been trying, for decades, to figure out just how many planets out there might actually resemble ours. For most of our species' story, that question wasn't even scientific. It was philosophical, or theological, or the stuff of rumor and myth. We could track the 5 wandering lights we now know as planets in our own sky, but the stars beyond were only points of light, with no visible companions. The first confirmed planet found circling another star. A true exoplanet wasn't announced until the early 1990s. Since then, the tally has climbed into the thousands, with new ones added so regularly that it's hard to keep the mental list updated. Many of them look nothing like Earth at all. Bloated gas giants, worlds skinned in molten rock, frozen balls on the edge of space. But some are eerily similar in size and orbital distance. A few even lie in what we call the habitable zone, the range where liquid water could exist. That term, though, is easy to misunderstand. The habitable zone doesn't certify a planet as actually habitable. It just says that if other things go right, water could be liquid on its surface. You can be at the perfect distance from your star and still be hopeless. A world might lack an atmosphere entirely, or be wrapped in one full of poisons. It could sit at just the right temperature, but have no magnetic field, leaving its surface blasted by radiation. It might be an endless water world with no land, or a rocky globe with almost no water at all. From what we're learning, getting all the pieces into the right configuration and then keeping them there is far harder than it first sounds. Earth, in that sense, is perched on a narrow, precarious ridge between extremes. Move us appreciably closer to the sun, and we start edging toward a Venus-like hell. Shift us farther, and we risk becoming a frozen Mars. Make us much smaller, and we likely lose our air to space. Make us much more massive, and our surface could become a crushing, super-dense world instead of a relatively gentle one. Even details like the tilt of our axis, the size of our moon, and the gravitational presence of Jupiter, which seems to intercept or redirect many potential impactors, turn out to matter. The more we study planetary science, the more it seems like there's an exhausting checklist of conditions a world must keep meeting for billions of years before something like us can appear. And yet, there are so many stars and so many planets that at least some slice of them must tick enough boxes. If Earth isn't the only one that has done this, then it's reasonable to imagine other Earth-like worlds existing in the past. And if some of those worlds aren't living now, we're left with a question that's hard to ignore. What went wrong? Were those planets undone by forces no one could have controlled, like a star that slowly brightened until it cooked its inner worlds? Or a catastrophic asteroid impact at precisely the wrong time? Or were they undone from the inside by their own life forms, perhaps intelligent ones, pushing the planet's systems past the point where they could recover? That can all sound very abstract until we bring it back to something we know. Picture yourself on a coastline here on Earth looking out across the ocean. You know the waves will keep rolling in and out. Tides will rise and fall. Storms will come and pass. The shoreline might creep over centuries, but right now it feels steady. Permanent even. Now transplant that scene onto another world. Same rocky shelf. Same sweeping curve of what used to be a shore. But the water is gone. The basin is dry and cracked. The air is thin or caustic. The sun above looks off too bright, too dim, the wrong color. There is still a stark beauty in that emptiness, but it's carried on a silence that hints at something that once was and is no more. That's what a failed world really is. Not always shattered or obliterated, but stripped of the ability to support what it once did. In our own neighborhood, Mars is the clearest candidate for this kind of story. We see dried up river channels slicing across its surface, minerals that can only form in the presence of water, caps of frozen ice at its poles. Billions of years ago, all of that points to a thicker atmosphere and a warmer climate. Then something changed. Mars's interior cooled, its core stopped powering a global magnetic field. Without that shield, the constant stream of charged particles flowing out from the sun, the solar wind began to scour away its atmosphere. As the air thinned, pressure at the surface dropped, and liquid water could no longer remain for long. It froze, seeped into the ground, or drifted away into space. If life had ever started there, it would have watched its window of opportunity narrow, decade by decade, millennium by millennium, until the surface simply became too hostile to endure. Today, Mars is a frozen desert. Whatever long story it has to tell is locked away in stone and dust. Venus is a different kind of warning. It may have opened its life as a world draped in oceans as well. But being closer to the sun and subject to a runaway greenhouse effect, it transformed into a furnace. Its atmosphere is almost pure carbon dioxide, trapping heat so effectively that its surface glows with temperatures high enough to melt lead. Clouds of sulfuric acid swirl overhead. The air presses down with more than 90 times the pressure of Earth's surface. Whatever chances Venus once had, they dissolved in a cascade of heat and chemistry that, once triggered, could not be reversed. Together, Mars and Venus remind us of something uncomfortable. Simply being in the right orbital band at the right time is not enough. Conditions evolve, sometimes slowly, sometimes in sudden lurches. A planet that seems steady for hundreds of millions of years can creep over a threshold and never come back. That's part of what makes Earth's long run as a habitable world so remarkable. We've taken asteroid hits, we've endured ice ages and violent swings in climate, and yet we've managed so far to avoid being pushed off the narrow ridge we're walking. Zoom that view out to the scale of the galaxy, and things get more complicated still. Some stars are far more volatile than our sun, shedding flares and radiation bursts that could peel away a planet's atmosphere in a geologic instant. Some planetary systems are gravitationally unstable, their worlds tugging and jostling until orbits shift and everything changes. Other planets form in chaotic regions, dense clusters of stars, or neighborhoods near frequent supernovas, where destructive events are simply more likely. The environments that let life ignite are delicate. The environments that let it endure are rarer still. If you picture the galaxy as a landscape, it's not a flat plain with a few scattered oases of life. It's more like a jagged mountain range filled with deep, frozen valleys where conditions are too harsh, sharp peaks where favorable conditions are brief, and a few broad plateaus where life can get its roots into the ground and spread. Earth may be standing on one of those plateaus at the moment. But plateaus erode. On timescales of millions or billions of years, climates reconfigure themselves, continents wander, stars quietly transform. Our own sun will one day swell into a red giant, roasting or swallowing the inner planets. Long before that, Earth's habitability will shift in ways we may not be able to fully counter. All of this leads to a deeply logical, if unsettling, idea. Many planets that would have looked like Earth in their prime probably don't look that way anymore. At a glance, they might still seem promising, checking the boxes for size and orbit, but on closer inspection, they've slipped past their moment. They are, in a sense, cosmic houses with their lights still on, but no one left inside. And if the galaxy has been around long enough for this to happen again and again, then it may be that we're living in a universe already full of such houses, quiet, intact, and empty. This doesn't have to make us despair. It can just as easily deepen our gratitude. The simple fact that Earth is still in its habitable window suggests we are experiencing something that may not be common at any given moment in cosmic time. It also means we're in a position most planets never reach. We can recognize our own fragility, and we can choose how we respond. Other worlds may never have had that chance, or they did, and didn't recognize it until it was gone. We do. And that's where our journey through the lives and deaths of planets really begins. Because if we want to understand Earth's possible fates, we have to understand how worlds fail. That path starts close to home and then stretches out into the greater galaxy, where the patterns in those failures begin to reveal themselves. If you could drift above the Milky Way and look down on it from the outside, you'd see a vast, spiraling river of light. Hundreds of billions of stars stitched together by dark lanes of dust and tendrils of glowing gas. Seen that way, from a God's eye distance, it would be easy to assume that in all that abundance, life must be everywhere. How could it not be, with so many stars, so many planets, so many places for chemistry to get interesting. But between those bright points, there would also be an enormous amount of darkness. In that darkness, hidden from all but the most careful observers, lie places that once might have been alive in ways we can hardly picture, and are now nothing more than remnants. You could think of them as markers in a cosmic cemetery, gravestones without inscriptions anyone has ever read, scattered across incomprehensible distances. This is what we at Echoes of the Forgotten Earth like to call the graveyard of planets. That phrase isn't part of formal astronomy. Scientists talk about uninhabitable or sterile worlds, words that sound clinical and detached. Graveyard carries a different weight. It implies that something has been lost, that there was a before and an after. It hints that many of the planets we study today might not simply be places where life never appeared, but places where life failed to last. We don't recognize them as such because we arrived late. We only see them in their final chapters, having missed the opening pages entirely. Some of these dead planets likely never had much of a chance. They formed so close to their stars that their surfaces were torched from the beginning, or so far away that they froze solid before anything dynamic could happen. Others circled stars that lived quickly and died violently, swelling into giants or exploding and leaving their planets scorched, swallowed, or flung into interstellar space. But the most haunting residents of this graveyard are the ones that look like they could have made it. The ones that had the right mass, the right temperatures, the right positions. Maybe even oceans and atmospheres that could have sustained life for millions, tens of millions, or even hundreds of millions of years. And yet, they didn't endure. Venus and Mars, our own local ghosts, are the gravestones we can visit most easily. Their stories are sobering. They show us that stability is fragile and that once it breaks, the forces that held it together don't just quietly restore themselves. On Venus, the greenhouse effect we rely on here to stay warm spun out of control. Carbon dioxide accumulated, trapping more heat. That extra heat freed even more CO2 from rocks and surface materials, which trapped still more heat. Once that runaway process crossed a certain line, there was no realistic path back to something like Earth. On Mars, the opposite unfolded. Its interior cooled, its dynamo shut down, its magnetic field faded. Without that magnetic barrier, the solar wind had direct access to its atmosphere. Over millions of years, that invisible gale stripped away much of its air. The remaining gases thinned into a whisper. The warmth followed. What liquid water there was retreated into ice or escaped. Whatever habitability Mars once enjoyed gradually withered. 2 worlds, 2 thresholds crossed, 2 no-return points. Those are just the closest examples. With the thousands of exoplanets we've cataloged so far, we're starting to glimpse larger patterns. Many of the worlds we've found huddle so close to their stars that they're tidally locked one side in perpetual scorching daylight, the other in frozen night. The day side may be blasted and bare, the night side encased in ice, with only a narrow twilight ring in between where temperatures might be bearable. That sliver is hardly enough for a stable, planet-wide biosphere. Other planets are massive gas giants with no solid surface at all, or rocky bodies stripped bare of atmospheres by fierce, stellar winds. Some are super-Earths, larger than our planet, orbiting in what appears to be a habitable zone. On paper, they sound ideal. In reality, many may be smothered under crushing atmospheres, or covered in oceans so deep and global that there's no exposed land, radically changing their climate and chemistry. Some might have been habitable once, only to lose the balance that made them so when their stars brightened or their own geologies betrayed them. One of the more unsettling ideas in modern planetary science is this: even if a planet harbors life at one point in time, there's no guarantee life will be there later. Stars slowly brighten as they age. Continents move, mountains rise and erode, ocean currents reroute. A planet's atmosphere can gradually drift into a different composition. On Earth, life itself has rewritten the atmosphere at least once, flooding it with oxygen that was toxic to many earlier organisms. There's no rule that says the changes life triggers will always be to its own benefit. On another world, a biological revolution could easily drive the environment toward less habitable, not more. The graveyard likely doesn't just hold planets whose biospheres quietly ebbed away. Some worlds may have ended in sudden catastrophe. A single large asteroid impact can transform a thriving ecosystem into a wasteland in days to weeks. A nearby supernova can bathe a planet in high-energy radiation, hammering its atmosphere and damaging any surface life. A shifting giant planet in the same system can nudge a habitable world into a more eccentric orbit, plunging it into extreme seasons, or even hurling it out into the darkness between stars altogether. Imagine an ocean planet, full of life, slowly drifting away from its star after its orbit becomes unstable. The seas freeze from the top down. Atmosphere condenses or drifts away. The last open waters close. Life doesn't fade gently. It crashes into a permanent night it can't adapt to. From the universe's perspective, these scenarios aren't exotic. On cosmic timescales, they're ordinary risks. Planets are born into turbulent neighborhoods. They share space with other worlds that tug on them with invisible hands of gravity. They orbit stars that flare, pulse, and eventually die. They circle within galaxies where stars are born and destroyed in looping cycles of calm and violence. Right now, we live in a relatively quiet sector around a relatively stable star. But the universe, taken as a whole, is anything but calm. There's another wrinkle. The graveyard might not be entirely permanent. Some planets could, in theory, be brought back from the edge, or stumble into new habitability by chance. A frozen rogue world drifting through space might pass close enough to a star to warm back up. A planet that lost its air could, over immense time, regenerate an atmosphere from volcanic outgassing or repeated comet impacts. Whether life would arise again or reappear after hiding is a more complicated question. But habitability itself might rise and fall in waves. If that's true, then the graveyard is messier than it looks. Some entries might be more like "to be continued" than "the end." Still, for most of these worlds, the ending is final. A runaway greenhouse doesn't simply unwind on its own. A planet consumed by its star doesn't re-emerge elsewhere. A collision energetic enough to fragment a planet doesn't knit itself back together into the same world again. Even when the physical body of the planet survives, the end of its biosphere is the end of everything that made it alive, in the way we mean when we talk about living worlds. When we say dead planet, what we're really describing is the loss of possibility. These worlds might still be beautiful to look at, layered canyons, glittering ice caps, swirling clouds, but they no longer hold the potential for something that can grow, adapt, and transform its own environment. What makes the idea of a planetary graveyard so powerful is that it forces us to stop seeing worlds as static objects and instead as participants in stories, with beginnings, middles, and endings. Earth right now is in the middle passages of its story. We are living in the chapter where conditions still support oceans overflowing with life, continents dressed in forests and grasslands, atmospheres that let us breathe and shield us from the worst of space. The middle, though, is not the final page. And if Mars and Venus have anything to teach us, it's that endings come in many forms. The difficult part is that for almost every other world, we only ever see the last fragment of the story. We show up late. We pick through clues. We reconstruct what we can and guess at the rest. Even here, in our own system, that's how it works. Our picture of Mars's warm past is assembled from dry riverbeds and mineral deposits. Our reconstruction of Venus's transformation is drawn from its current climate and surface, not from direct records of what it once was. For distant exoplanets, this limitation is even sharper. With even our best telescopes, we're often inferring entire histories from a few pixels and a handful of spectral lines. It's like trying to read a eulogy from a name alone. There is a certain humility built into that. It reminds us that we're not the intended audience for these stories. The universe doesn't arrange its timeline so that we see neatly labeled causes and tidy conclusions. We might long for clean answers, exact dates, Precise mechanisms, clear blame. But the graveyard, as we're starting to glimpse it, doesn't give us that. It offers us patterns, not narratives. Probabilities, not certainties. It shows us how easily habitability can be lost, and hints, uncomfortably, that we're subject to the same physics and the same odds. So when we talk about a graveyard of planets, we aren't just indulging in poetic imagery or cosmic archaeology. We're also holding up a mirror. It's a warning, as much as it is a memorial. It shows us what can happen to worlds very much like ours, and quietly asks where we think we fit in that enormous, unfinished catalog. Are we the rare outlier that manages to survive far longer than the average? Or are we simply one more planet marching toward a future we'd rather not envision? The only honest way to begin answering that is to get closer to the individual stories of these lost worlds, to look, as carefully as we can, at the neighbors that share our star, to read the traces written into their rocks and skies, and to let them tell us what they can about the path we're walking. Some of those stories are literally next door, waiting patiently for us to piece them together. When we imagine ghost worlds, our minds usually leap to far-off exoplanets, tiny silhouettes crossing the faces of distant stars, or faint gravitational tugs revealed only in complex data. But the truth is, we don't need to gaze across the galaxy to find examples. Some of the most compelling ghost worlds orbit the same sun we do. They share our celestial address. They're close enough that we've sent machines to them. We've photographed their surfaces in detail, rolled robotic wheels across their dust and dipped through their atmospheres. The more intimately we get to know them, the more they resemble ruins scattered around our own neighborhood places that might once have been alive in some sense, and now float on as hollow shells. Mars, Venus, and several of the solar system's larger moons all fall into this category. Each carries a different version of how a world can go from promising to desolate. Together they form a small but powerful collection of case studies in planetary failure. And because they're nearby, they're our clearest windows into what went wrong. Even so, there's more we don't know than what we do. Mars is probably the most famous of these ghosts, partly because of how uncannily Earth-like it seems in some ways. It's smaller, colder, and drier now, but it still has canyons, volcanoes, ice caps, and weather. The wound-like shapes of old river valleys cut across its surface. All of it points toward a past that was markedly different from the airless, dusty world we know today. A past in which liquid water could flow across the surface and collect in lakes or shallow seas. Orbital data and rover findings have strengthened that picture again and again. We've found clays and minerals that only form in water. We've discovered layered rocks that look like sediments laid down at the bottoms of ancient lakes. All of it implies that Mars once had a thicker, warmer atmosphere and a climate that could support stable bodies of water. The leading idea is that Mars lost most of that atmosphere when its magnetic field faded. Without that invisible protective bubble, the solar wind had a clear shot at its air, gradually stripping it away. As the atmosphere thinned, surface pressure dropped, and liquid water became unstable. It either froze into the ground and polar caps, or slowly escaped to space. Whatever life might have begun there, if it did at all, would have faced a steadily worsening set of conditions. The comfortable era, if it existed, shrank and then vanished. Today, Mars still harbors water, but mostly as ice, and possibly as briny subsurface reservoirs. At the surface, radiation is intense, the air is thin, and the cold is relentless. If anything survives, it likely does so deep beneath the ground. Venus, by contrast, is a tale of too much heat rather than too little. It's remarkably similar to Earth in size and composition, which once led scientists to imagine it as our twin in habitability. Instead, it has become one of the harshest environments we know. If Mars is a cold tomb, Venus is a furnace. Both outcomes are written into our sky, orbiting the same star we do. And then there are the moons, Europa, Enceladus, Titan, and others worlds that were never quite like Earth on the surface, But that may hold liquid oceans and interesting chemistry hidden below ice and haze. They aren't failed Earths in the classic sense, but they are almost worlds, perched just on the edge of what we might call habitable. Studying this small circle of ghostly neighbors is more than planetary tourism. It's our clearest, most immediate way to learn how fragile habitability is, how many paths there are to failure, and how thin the line really is between a living world and a silent one. And with that understanding, we can start to look farther out toward the exoplanets we can't yet touch, to see how many of them might be echoes of these same stories, playing out on other stages around other suns. Mars has lived in our imagination for as long as we've been watching the sky. Long before telescopes, people noticed its reddish glow and its odd looping path among the stars. Different cultures gave it the names of their war gods, their emblems of power and blood, as if they could sense something unsettling in its color and motion. As our understanding of the solar system grew, Mars became the obvious candidate for another Earth, a nearby world that might have life, or might have had it in the past. Over time, our view has swung like a pendulum between thinking of it as a living neighbor and a dead rock. But the more we study it with clear eyes, the more the truth seems to sit somewhere awkwardly in the middle. Mars today is, as far as we can tell, lifeless at the surface. But the evidence that it was once far more hospitable keeps stacking up. Those early hints came not from landers, but from telescopes. In the late 1800s and early 1900s, astronomers like Giovanni Schiaparelli and Percival Lowell spoke of linear features they thought they could see on the Martian surface. They called them canals, a word that carried enormous weight. It conjured visions of intelligent Martians digging vast waterways to move precious water across a dying world. We now know those canals were illusions, tricks of optics and expectation. But the narrative they spawned got its hooks into our collective imagination and never really left. The reality revealed by spacecraft turned out to be quieter and, in many ways, more profound. Mars does have channels and valleys that stretch for hundreds or thousands of kilometers, but they weren't engineered. They were carved by rivers and floods. When NASA's Mariner mission sent back the first close-up images in the 1960s and 70s, Mars looked at first like a more interesting version of the Moon. Dry, pocked with craters, seemingly inert. For those who had dreamed of forests or cities, it was a letdown. But scientists quickly realized that underneath that barren impression, there were clues. Viking orbiters in the late 1970s showed branching valley networks, floodplains, and sediment fans, features that on Earth are shaped by flowing water. Later missions like Mars Global Surveyor, Mars Odyssey, and a series of increasingly capable rovers sharpened that picture. Billions of years ago, Mars likely wore a thicker atmosphere and enjoyed warmer temperatures. It probably hosted rivers, lakes, and maybe even shallow seas. One of the most compelling lines of evidence comes from minerals. Rovers and orbiters have found clays and hydrated salts scattered through the Martian crust. Those minerals form only in the presence of water. Curiosity's exploration of Gale Crater revealed layered deposits that look strikingly like lake sediments on Earth-thin beds piled over vast distances, recording cycles of wet and dry that may have played out over millions of years. If life ever appeared there, those ancient lakes would have been prime habitats. So what severed that possibility? The leading explanation comes down to size and heat. Smaller planets lose their internal warmth faster than larger ones. As Mars cooled, its core likely stopped generating the magnetic field that once enclosed it. Without that shield, the solar wind could strip away the upper atmosphere bit by bit. As the air thinned and surface pressure dropped, liquid water could no longer remain in open contact with the sky for long. It froze into the ground, collected in ice caps, or bled off into space. Over geological time, Mars shifted from a warm, wetter world to the cold desert we see now. If a biosphere had begun, its habitable zones would have retreated underground, then shrunk toward nothing. It's still possible that microbial life lingers beneath the surface, sheltered from radiation and cold within rock and ice. Periodic detections of methane in the Martian atmosphere, some of it variable with the seasons, have stoked speculation. On Earth, much methane is produced by biology. But non-biological processes can generate it too, through interactions between water and rock. Right now, methane on Mars is a tantalizing question mark, not an answer. That's part of what makes Mars so important in our search for life beyond Earth. If we ever find direct evidence of ancient microbes in its rocks or unmistakable chemical signatures of past biology, it would mean that life arose independently twice in the same solar system. That single fact would dramatically raise the odds that life appears wherever conditions permit. But such a discovery would also highlight a harsher truth. Habitability can be temporary. A planet that gets everything right for a while can still lose its grip. What's striking about Mars is not just how different it is from Earth now, but how similar the two worlds might have been early on. Both formed from the same swirl of dust and gas around the infant sun. Both had volcanism, liquid water, and atmospheres. For some period, they may have been near twins, each with a real chance to develop life. Then their paths diverged. Earth kept a strong magnetic field. Its atmosphere stayed thick enough to protect surface water. Its climate, though it has swung wildly at times, has remained within the bounds where liquid oceans can persist. Mars lost its field, lost most of its air, and slid into deep cold. We can only estimate how long Mars's habitable window lasted. Maybe a few 100 million years. Maybe over 1 billion. Either way, in cosmic terms, that may not be enough time for complexity to evolve much beyond microbes. That raises a sobering possibility. The universe might be crowded with planets where life began, but never got the time it needed to grow complicated. Worlds where biology made it to the microbial stage, maybe even to simple multicellular forms, only to be erased by climate shifts, atmospheric loss, or other slow-moving disasters. From a distance, Mars still tempts us. Its landscapes look familiar in photographs. Its volcanoes tower higher than any on Earth. Its canyon system, Valles Marineris, puts our own rifts to shame. Its skies grow hazy with dust, and thin water ice clouds drift overhead. If you stood there in a protective suit, you might catch yourself forgetting where you are just for a heartbeat. But the illusion would break quickly. The air is so thin you'd suffocate in seconds. Nighttime temperatures often plunge low enough for carbon dioxide itself to frost out of the atmosphere. Global dust storms can enshroud the entire planet, dimming the sun for weeks. It is, undeniably, beautiful. And it is also unforgiving. What we see on Mars today is the aftermath of a long decline. Its rivers have been dry for billions of years. Its seas, if they ever existed at the surface, are gone. Its once protective atmosphere has faded into a fragile veil. Yet in its rocks and sediments, the record of that earlier era remains. Rovers scraping and drilling at its surface are, in a sense, archaeologists of a world that nearly made it. Mars forces us to confront how close a planet can come to being Earth-like and still end up nearly dead. It reminds us that planetary conditions are not fixed, and that what is true today may not be true tomorrow, especially when we zoom out to geological timescales. Earth's own atmosphere, oceans, and climate have changed dramatically over billions of years, and they will continue to evolve. The difference so far is that our planet has stayed inside the narrow band where complex life can survive and adapt. Mars fell out of that band. We're still reconstructing exactly how and when, but its story is a cautionary line in the cosmic ledger. If humans do eventually walk on Mars, they'll be stepping into a fossil planet. They'll stand where water once ran freely, where the sky might have been thicker and bluer, where life may have been getting its start while Earth was still young and chaotic. They'll watch a smaller, dimmer sun cross a salmon-colored sky, feel the pull of weaker gravity, and know, if they're honest with themselves, that they are wandering across a monument to planetary fragility. That's why Mars, for us at Echoes of the Forgotten Earth, is more than a destination. It's a parable written in dust and stone. It shows that being habitable once doesn't guarantee being habitable forever. As we keep exploring it, we're not just searching for ancient microbes. We're collecting data on how a promising world can fail. And that understanding naturally turns our attention to the opposite extreme in our sky, a world that didn't freeze into silence. but burned itself into a trap. If Mars is a lesson in what happens when a planet loses too much warmth and air, Venus is the lesson in what happens when it keeps both, but in the wrong way. Venus sits close enough in size, mass, and basic ingredients to Earth that we often call the two planets twins. In the early decades of planetary science, it was reasonable to picture Venus as Earth's sister in climate as well, maybe wrapped in clouds and forests beneath the haze, maybe home to warm oceans and thick, breathable air. Instead, we found one of the most extreme environments in the solar system. Today, Venus's surface is hot enough to soften metal. The pressure at ground level would crush you like a deep ocean trench. The air is almost entirely carbon dioxide, laced with droplets of sulfuric acid. It's a world where the very atmosphere is a weapon. What makes Venus especially compelling, and especially unsettling, is the likelihood that it didn't start this way. Many planetary scientists suspect that billions of years ago, Venus could have had liquid water on its surface. Its similarity to Earth suggests that both planets may have begun with comparable water inventories and similar early atmospheres. The turning point seems to lie in Venus's orbital position. It's about 30% closer to the Sun than Earth is, which means it receives almost twice as much solar energy. On Earth, we sit in a range where the interplay between incoming sunlight and outgoing heat keeps global temperatures in a band where liquid water can persist at the surface. On Venus, that extra energy may have nudged things into a different regime. As the young Venus warmed, more water would have evaporated into its atmosphere. Water vapor is itself a potent greenhouse gas. The more vapor in the air, the more heat is trapped. The more heat, the more evaporation. This positive feedback loop can, under the right conditions, accelerate rapidly. Over time, that runaway greenhouse may have boiled away Venus's oceans. High in the atmosphere, water molecules were broken apart by ultraviolet radiation from the sun. The light hydrogen escaped to space. With water gone, there was nothing left to effectively lock up carbon dioxide and rocks. CO2 built up in the atmosphere instead, thickening into an enormous insulating blanket. The result is the Venus we see now, an atmosphere composed almost entirely of carbon dioxide, over 90 times denser than ours at the surface, trapping heat so effectively that Venus is hotter than Mercury, despite being farther from the Sun. Above that inferno, clouds of sulfuric acid swirl, reflecting much of the sunlight that hits them. That's why Venus is so bright in our sky, a brilliant evening or morning star. For much of human history, it was an object of wonder and beauty. Many cultures associated it with love, fertility, and goddesses of light. Yet that glow hides a killing ground. Our attempts to reach the surface of Venus have been short and brutal. The Soviet Venera landers in the 1970s and 80s managed to touch down and transmit images, but none survived longer than a couple of hours. They were crushed, cooked, and corroded nearly as soon as they arrived. The pictures they sent before failing show a landscape of fractured rocks under a dim yellow sky. No seas, no gentle clouds, no sign of anything alive. Later missions, like NASA's Magellan orbiter, used radar to pierce the cloud layer and map the landscape. They revealed broad volcanic plains, highland regions, and thousands of volcanoes. Some of those volcanoes may still be active today, feeding the dense atmosphere with fresh gases. We still don't know exactly when Venus crossed from maybe habitable to definitely not. Some climate models suggest it might have enjoyed relatively mild conditions, perhaps for hundreds of millions, or even over 1 billion years, before tipping into its current state. If that's true, then Venus had a long window during which life could, in principle, have arisen. That possibility carries heavy implications. It says that even a world with oceans and a temperate climate for a very long time can still fall into a spiral it can't escape. There is no permanent membership card for the Habitability Club. For Earth, Venus is a glaring cautionary tale. Yes, we're farther from the Sun. Yes, our atmospheric history is different. But the fundamental physics that drove Venus into a runaway greenhouse are the same ones we use to understand our own climate. Runaway warming, loss of water, shifts in atmospheric chemistry. These aren't alien ideas, They're the same processes we model when we worry about adding greenhouse gases here. On Venus, they're simply played out to an ultimate conclusion. Venus also complicates how we search for habitable worlds around other stars. From far away, a Venus-like planet can look a lot like an Earth-like planet. Same size, thick atmosphere, orbit within what might seem like a habitable zone. If all we can see is a silhouette and some broad spectral hints, it's easy to mix them up. Understanding Venus in detail, how and why it failed, is crucial if we want to avoid false positives in our hunt for other Earths. We need to know what a doomed twin looks like from a distance. There's another reason Venus keeps drawing scientific attention. The possibility, still controversial, that life might exist there in some form even now. Not on the surface, where conditions are ferociously hostile, but high in the clouds. Around 50 kilometers above the ground, temperatures and pressures are much closer to those at Earth's surface, and there are molecules like water vapor present in small amounts. In 2020, a team reported possible evidence for phosphine gas in Venus's atmosphere. A molecule that, on Earth, is largely associated with biological processes. The claim has since been heavily debated, reanalyzed, and challenged. The data remain ambiguous, but the discussion itself shows how little we truly know about our neighbor and how easy it is for it to surprise us. For Echoes of the Forgotten Earth, Venus is the archetype of a world that had the ingredients to thrive and turn them into a trap. Its dense atmosphere keeps it fiery. Its heat may fuel ongoing volcanism, which in turn helps maintain that atmosphere. The planet is caught in a self-sustaining loop, but one that sustains only its own hostility. If Mars is a frozen tomb, Venus is a burning prison. And yet both are invaluable to us. They bracket Earth on either side, one too cold and thin, the other too hot and thick. Studied together, they sketch out the narrow corridor of conditions we currently walk through. Beyond them, there are other worlds that complicate the picture, further places that might never have been fully habitable on the surface, but that could hide life in protected pockets. To find them, we have to look not at planets, but at moons. Because in our solar system, some of the most intriguing places for life don't orbit stars at all. They orbit the worlds that orbit the stars. When we think about where life might exist, our instincts almost always go straight to planets. That bias is understandable. Earth is a planet. Every living thing we know about lives here. So when we look outward, we tend to look for other Earth's rocky spheres circling their stars at just the right distance. But if we pay close attention to our own solar system, something surprising emerges. Some of the most promising candidates for habitability aren't planets at all. They're moons. These aren't just passive ornaments, little rocks trailing after giant planets as they parade around the sun. Some of them are worlds in their own right, wrapped in ice, swaddled in thick atmospheres, hiding oceans or strange chemistry that might support life in forms we've never seen. Their stories don't mirror Mars or Venus. They've never had broad, sunlit continents, open blue seas, or skies you could breathe at the surface. They've grown up under extremes, permanent deep freeze, crushing radiation belts, orange smog, or endless distance from the sun. From the outside, most of them look dead. But beneath their surfaces, under ice shells, below oceans of hydrocarbons, within the warmth of tidal heating, there may be or may once have been conditions where life can take hold. These are the almost worlds. They never quite cross the threshold into full, surface-level habitability like Earth, but they brush against that border enough to make us wonder. Europa, one of Jupiter's largest moons, is one of the clearest examples. At first glance, it's a smooth, bright marble of ice. Its surface is scarred with dark streaks and tangled fractures, as if someone scratched it over and over with a knife. Impact craters are relatively rare, suggesting the surface is young and constantly being repaved. What makes Europa special, though, isn't what we see. It's what we infer. Beneath that icy shell, evidence points to a global ocean of liquid water kept from freezing solid by heat generated inside the moon itself. Europa orbits deep within Jupiter's gravitational field, and that immense pull flexes the moon's interior as it moves along its slightly elliptical path. That flexing creates friction, which produces heat. The result: a buried ocean that may hold more liquid water than all of Earth's oceans combined. Water alone doesn't guarantee life, but it's one of the key ingredients as we understand it. Europa also likely has a rocky seafloor where water meets stone. On Earth, such boundaries, especially around hydrothermal vents at the bottom of our oceans, host dense communities of organisms that live entirely off chemical energy, never seeing a single photon of sunlight. They feed on reactions between hot fluids and rock. If Europa has similar vents, its hidden ocean floor could be a cradle for life. Not life that looks like us, but something microbial, something adapted to darkness and pressure and chemistry instead of light. Enceladus, a much smaller moon of Saturn, offers another astonishing hint. For a long time, it was just another icy speck in the catalogs. Then the Cassini spacecraft flew past and saw something no one expected: towering plumes of water vapor and ice jetting from fractures near its south pole. These geysers spray material hundreds of kilometers into space. Cassini flew through them and sampled their contents. In those frozen grains, we found salts, organic molecules, and signs of water-rock interaction, everything you'd expect if there were a liquid ocean in contact with a rocky core below the ice. Like Europa, Enceladus seems to host a subsurface ocean kept warm by tidal heating. Unlike Europa, it kindly ejects bits of that ocean into space for us to taste. In terms of habitability, that's an invitation. We don't have to drill through kilometers of ice. We just have to fly through the spray and look closely. Then there's Titan, Saturn's largest moon. Titan is unique in another way. It's the only moon we know with a thick atmosphere, denser at the surface than Earth's. The air there is mostly nitrogen, like ours, but laced with methane and complex organics. The surface temperature hovers around 179 degrees, far too cold for liquid water to exist in the open, but other liquids can flow there. When we first mapped Titan with radar and infrared instruments, we found rivers, lakes, even seas, not of water, but of liquid methane and ethane. Titan has a working hydrocarbon cycle: methane rain, methane rivers, methane lakes, methane evaporation, methane clouds. It's like a mirror image Earth, with water frozen into rock-hard ice and hydrocarbons playing the role of water. Beneath that exotic weather, models suggest Titan may also hide a subsurface ocean of water mixed with ammonia. That means Titan might host two very different kinds of potentially habitable environments: a deep water ocean we'd feel slightly more at home with, and a surface world that could, in theory, support life with an entirely different chemistry based on liquid methane. If such methane-based life exists, it would rewrite our definition of habitable. Other moons add their own possibilities: Ganymede and Callisto around Jupiter, Triton around Neptune, all show hints they may contain buried oceans. We know less about them than we do about Europa or Enceladus, but they contribute to a growing realization. Habitability might not be a privilege reserved for planets in a neat ring around their stars. It might thrive in pockets beneath ice, circling gas giants far from the traditional habitable zone. These moons blur our tidy categories. They show us that judging a world's potential by its surface is risky. A moon can look dead from the outside and still shelter rich, dynamic environments within. The line between a failed world and a still viable one can be completely hidden from a casual glance. Unlike Mars or Venus, the icy moons were never truly Earth-like in the open. They never had blue skies and sprawling continents. Their almost status comes from the fact that they may harbor all the critical elements for life: liquid solvents, energy sources, complex chemistry, not on the surface, but in protected inner realms. If life can arise and endure in those interiors, it means the universe's inventory of living worlds could be far larger than we thought. Life wouldn't be limited to planets basking in the right amount of starlight. It could flourish in darkness, warmed from within. The challenge, of course, is proving it. Europa's ocean is sealed under tens of kilometers of ice. Enceladus's plumes, while generous by cosmic standards, are still subtle and intermittent. Titan's surface is masked by a dense haze, and its internal ocean is even harder to access than Europa's. Every one of these environments is a technical challenge that would stretch our engineering to its limits. But we're moving in that direction. NASA's Europa Clipper mission, set to launch in the near future, will perform dozens of close flybys of Europa, mapping its surface in unprecedented detail and searching for signs of active plumes that might connect the ocean to space. Other mission concepts envision returning to Enceladus to sample its geysers more deeply, or sending flying drones and floating landers to Titan's lakes to taste their chemistry from the inside. These efforts aren't just about checking a box that says life found or life absent. They're about understanding how many different environments can support at least the first steps of biology. If even one of these moons turns out to harbor living organisms, microbial mats in a dark ocean, strange chemical networks in a methane lake, it would tell us that life is flexible, that it doesn't require Earth-like surfaces or even Earth-like solvents. That, in turn, would reshape how we see the graveyard. A planet or moon that looks dead from afar might, in fact, still be alive below, quietly working through its own hidden chapters. At the same time, the almost nature of these moons reminds us how delicately balanced they are. If Europa's tidal heating were a bit weaker, its ocean might have frozen solid eons ago. If Enceladus vented less, we might never suspect its sea exists. If Titan lacked its thick atmosphere, its surface methane would vanish, and it would join the ranks of more ordinary frozen rocks. Whatever habitability they have is precarious. A shift in orbital resonances, a cooling of interiors, a change in tidal forcing, and their internal oceans could freeze, or their chemistry could stall. In the larger context of whether Earth is just one of many nearly failed worlds, these moons add nuance. Habitability isn't a simple binary. Worlds can exist in gray zones, where life thrives in margins while the surface looks dead, or where the components for life are present but never quite assemble into biology before conditions drift too far. They also hint at a difficult truth. If life can arise in such hidden places, it can also vanish there without leaving obvious traces. An ocean that hosted life for hundreds of millions of years could freeze over and lock its fossils in darkness forever. From the outside, we'd never know. In that sense, the moons that almost made it are both hopeful and haunting. They broaden our sense of where life might live, and they underscore how easily those habitats can wink out. From here, our journey through failed and fragile worlds pulls back from our solar system entirely. We've walked the dry riverbeds of Mars in our minds, walked through the heat of Venus, and dipped our thoughts into the buried seas of the icy moons. Now, we turn to the larger question. Not just where individual worlds succeed or fail, but how often the universe has tried to make something like Earth, and how often it has given up. To get there, we have to talk about odds. When we look at our own system, we see an odd little sample set. One lush, complex biosphere, one frozen former contender, one runaway hothouse, a collection of icy, almost worlds with secret oceans, all orbiting the same star, all forged from the same cloud of material, all ending up in radically different states. That variety is a hint that the road to a stable, living planet isn't straightforward. It's a tangle of coincidences and constraints, a long shot that has to keep paying off again and again for billions of years. At Echoes of the Forgotten Earth, we sometimes call this the cosmic lottery. When we look closely at our own solar system, we see a small but revealing spread of outcomes. There's Earth, teeming with life and dizzying variety. There's Mars, which seems to have once been warmer and wetter, but is now locked in cold and dust. There's Venus, which may have worn oceans long ago, but is now an inferno, wrapped in carbon dioxide and acid clouds. There are the icy moons, some hiding deep oceans that might be full of promise, others frozen and still. All of these worlds orbit the same star, all condensed from the same swirling disk of dust and gas, yet each followed a radically different path. That diversity is easy to overlook because we're so used to seeing only our own perspective. but it's a powerful reminder. The conditions that make a planet comfortably habitable are not only rare in space, they're also the result of a long sequence of chances stacking the right way. That's where the idea of the cosmic lottery comes in. Imagine the birth and evolution of a solar system as a series of astronomical coin flips and dice rolls. The initial composition of the nebula, the exact distances at which planets form from their star, the timing and violence of early impacts, the tilt of each planet's axis, the presence and strength of magnetic fields, the mixture of greenhouse gases in each atmosphere, the size and orbit of any moons, the arrangement and stability of neighboring planets. Every one of these factors nudges a world toward or away from long-term habitability. Change any of them enough, and the outcome shifts. Earth, in this view, is a planet with an improbably long run of favorable draws. Our distance from the sun keeps temperatures in the range where liquid water can exist at the surface. Our atmosphere is thick enough to retain that water in moderate temperatures, but not so thick that it cooks us. Our magnetic field shields us from solar and cosmic radiation. Our unusually large moon helps stabilize our axial tilt, preventing wild climate swings. Our plate tectonics slowly recycle carbon, acting as a planetary thermostat over geologic time. Even the chaos of asteroid and comet impacts has cut in our favor. They delivered water and organic materials, but not so frequently or so massively as to sterilize the planet completely after life began. But none of this was guaranteed. Move Earth a little closer to the sun, and we might have fallen into a Venus-like runaway greenhouse. Move us farther out, and we might have become a frozen Mars analog. Take away the moon, and our tilt could have lurched chaotically over millions of years, pushing climates into extreme patterns. Remove the magnetic field, and the solar wind might have eroded our atmosphere to a fraction of its present density. Turn off plate tectonics, and we might have locked ourselves into a permanent snowball or hothouse. Now scale that idea up from one system to the galaxy. Hundreds of billions of stars, likely trillions of planets. Many of them probably start the game with at least some of the raw ingredients for habitability. Rock, volatiles, a decent orbit. But the odds of hitting the full combination of conditions and then maintaining them for billions of years are still low. Even for planets that get the early draws right, the game doesn't end. The lottery keeps running. A world has to keep winning again and again for as long as complex life needs to evolve and survive. This shifts how we think about habitability, The habitable zone around a star where temperatures would allow liquid water is just the first filter. It's an invitation to play, not a guarantee of winning. The deeper test is temporal. Can a planet stay inside that narrow envelope of tolerable conditions long enough? The evidence from our own neighborhood suggests many worlds start off looking promising and drift out of that promise over time. Some fail early, like Venus might have, tipping into catastrophic greenhouse warming before life gains momentum. Others fail later, like Mars, losing atmosphere and liquid water after a stretch of relative habitability. For every Earth that manages to sustain a rich biosphere over billions of years, there may be dozens or hundreds of planets that almost made it, but ran out of time. There's another ingredient here: pure chance. Even with the best possible setup, right orbit, right atmosphere, right geology, things can still go sideways. On Earth, the asteroid that ended the age of dinosaurs could have been slightly larger or struck a different region and done far more damage. A nearby supernova could have bathed our planet in radiation at a vulnerable point. A tweak in volcanic timing could have driven us into an unrecoverable climate state. This doesn't mean life is hopelessly flimsy. Earth has already survived for more than 3.5 billion years with life intact. It does mean that resilience and luck are always intertwined. The planet's systems can absorb and buffer some shocks. Others are big enough that if they happen at just the wrong time, they rewrite everything. In the language of the cosmic lottery, you can stack the odds somewhat, but you can't control every draw. When we search for life elsewhere, we're effectively looking for other jackpot winners. But it's worth remembering, even big winners don't hold their tickets forever. Stars age, climates shift, planetary cores cool, orbits evolve. The question isn't only, does life exist somewhere else right now? It's also, how long does it last when it does appear? Picture the graveyard of planets again, but now populated not just with lifeless rocks, but with the ghosts of once living worlds. Some may have nurtured thriving biospheres for hundreds of millions of years before losing stability. Others may have only hosted microbial films in shallow seas before being knocked out of the habitable zone. For us, all of this carries a humbling implication. If we do find life elsewhere, microbial, complex, or even technological, it's likely to be just as temporary as ours, given enough time. There's no such thing as a permanently habitable planet. There are only worlds that are habitable for a while. It's tempting to believe that intelligence and technology can change that. That once a species reaches a certain level of understanding, it can protect its planet against the same fates that befell Mars, Venus, or countless unseen exoplanets. Maybe we can stabilize our climate, deflect dangerous asteroids, even one day move our civilization to other worlds as our star evolves. Those are real possibilities, but they address only some of the risks, and only if we manage them well. The cosmic lottery includes both the threats we can predict and those we haven't imagined yet. History, both planetary and human, suggests that surprises are inevitable. Right now, Earth is holding a rare winning streak. We're in the right orbital range, around a relatively calm star, with a climate that has been extraordinarily stable during the brief era of human civilization. We're here to notice that stability at all, which is itself remarkable. But the longer we study other worlds, the clearer it becomes that this streak is fragile. We are not the default outcome of planetary evolution. We're the result of a long string of contingencies, any one of which could have gone differently. As echoes of the forgotten Earth, we see the cosmic lottery not just as a metaphor for how rare living worlds are, but as a reminder. The odds never stop being in play. For every world that keeps winning long enough to tell a long story, many more flame out early or stumble halfway. Which leads us to a related and even more unsettling idea, one that doesn't just ask how rare living planets are, but how many of them ever get as far as we have. That idea is called the Great Filter. If the cosmic lottery is about getting the conditions for life started and keeping them going, the Great Filter is about the bottlenecks along the path, from simple chemistry to beings capable of asking questions about their own survival. Somewhere on that path, perhaps at several points, there may be steps so difficult that almost no world gets past them. We can outline that path in broad strokes. First, you need a planet or moon with the right raw materials and reasonably stable conditions. Then, in at least one niche, non-living chemistry has to cross the line into self-replicating molecules, what we might call the origin of life. From there, simple cells must arise, then more complex cells. Eventually, some of those cells must join together into multicellular organisms. Those organisms must, on at least one world, evolve nervous systems and intelligence. Eventually, at least one lineage must develop technology and the ability to transform its environment on a planetary scale. And then that technological civilization has to survive long enough to expand beyond its home world. The Great Filter is the idea that somewhere in that chain, there is at least one step that is extraordinarily unlikely. We talk about it mostly in the context of the Fermi paradox. If the galaxy is old and full of planets, and if technological civilizations can in principle arise, why isn't the sky obviously full of their signals and artifacts? One possible answer: the Great Filter is early. Maybe the origin of life is vanishingly rare. Maybe almost no planet ever sees chemistry cross that threshold from complex molecules to actual biology. In that case, most habitable planets are eternally empty oceans, atmospheres, and continents with no living things to experience them. If that's true, then Earth is exceptional simply because life started here at all. Another possibility is that the Great Filter is late. Maybe simple microbial life is fairly common, but the jump to complex multicellular organisms is rare. On Earth, life stayed microscopic for nearly 3 billion years. Complex life arose only in the last slice of our planet's history. Perhaps most living worlds are stuck in that earlier phase, forever alive, but never building brains or societies. Or the bottleneck might be intelligence itself. Complex animals might be common, but self-awareness, language, and tool use might be so improbable that they emerge only a handful of times across the galaxy, if that. Then there's the possibility many people find most disturbing. The Great Filter is ahead of us. In that picture, lots of worlds might successfully grow complex, intelligent life. Many might build civilizations, maybe even technologies far beyond our own. But almost none of them manage to survive their technological adolescence. They either self-destruct through war, environmental collapse, or uncontrolled technologies, or they fail to cope with natural changes they could have prepared for. If that's the case, then the graveyard of planets may contain many worlds that look, from a distance, like Earth does now. Worlds that once hummed with activity, built cities, sent signals into space, and then went quiet. Our own solar system shows us only the earliest parts of this sequence. Mars and Venus remind us how fragile the first step long-term habitability really is. The icy moons show that even when life's ingredients are present, they may never assemble into biology as we know it. None of our neighbors, as far as we can tell so far, made it to complex life, much less to a civilization. On Earth, life's timeline is instructive. If Earth formed about 4.5 billion years ago, the earliest fossil evidence for life appears not long after the crust cooled enough for oceans to form. That suggests the origin of life might not be the hardest step. It happened relatively quickly once the planet was ready. But for most of our planet's history, that life remained microbial. Multicellular organisms only appear in the fossil record in abundance in the last 600 million years. Humans, as a distinct species, have existed for perhaps 300,000 years. Our technological civilization, the kind that could meaningfully change the planet, has been around for only a few thousand. In other words, we are sitting at the very tip of an extremely long and narrow spike. This raises an uncomfortable possibility. Maybe the real Great Filter is not getting from chemistry to cells or from cells to animals, but from early civilization to long-term stability. Maybe many worlds reach the point where they can change their own planets rapidly, but almost none learn to do it without wiping out the conditions they depend on. Our own history offers a glimpse of the dangers. We've learned to split atoms, alter the atmosphere, rearrange genomes, and tap into vast stores of fossil energy. These abilities give us power to protect ourselves against some threats, and power to cause new ones. The same technology that lets us launch probes into space also lets us build weapons that could end our story in days. The Great Filter, if it lies ahead of us, could be something obvious. Managing nuclear arsenals, avoiding catastrophic climate disruption, preserving biodiversity. Or it could be something we haven't fully recognized yet. The long-term effects of new technologies, subtle changes in planetary systems that only become clear after it's too late, or social and psychological barriers that make sustained global cooperation nearly impossible. We don't know where the Great Filter is. We don't know if we've already passed it, if we're in the middle of it, or if it's still waiting for us in some distant century. But the more we study the graveyard of worlds, the more it looks like there are many ways to fail long before a species ever gets the chance to ask these questions. For Echoes of the Forgotten Earth, the Great Filter isn't just a theoretical exercise. It's a lens. It asks us to look at Mars and Venus and the near misses in our own system and see them not just as curiosities, but as reminders. Surviving long enough to look back on your own history is not a given. It's an achievement balanced on a knife's edge. From here, our attention turns from what the universe does to worlds, to what worlds with intelligent life do to themselves. Because some planets might not be undone by their stars or their orbits or their geology, but by the very minds that arose from their biospheres. And that is where the graveyard becomes not just a cosmic landscape, but a possible destination of our own making. When we picture extinction on a planetary scale, we usually imagine forces that life has no control over, tumbling rocks from space, furious eruptions, or distant stars exploding. But sometimes, the factor that ends a planet's long stretch of habitability isn't an outside blow. It's something that emerges from within the biosphere itself. A civilization can be the most elaborate expression of life on a world, and also the most dangerous thing that world has ever produced. Human civilization is, in planetary terms, a brand new phenomenon. Our species has existed for a fraction of Earth's history. Agriculture is only about 10,000 years old. The industrial era spans just a few centuries. In that incredibly short time, we've become capable of reshaping the atmosphere, changing the climate, and altering ecosystems on a scale that rivals some natural processes. We're not the first complex society to rise and fall here. History is full of local collapses. The Maya cities of Central America, the Indus Valley civilization, the culture that once flourished on Easter Island, the Western Roman Empire. Each rose to impressive complexity before unraveling. None of those collapses ended life on Earth. They didn't even end humanity. But they share patterns that matter when we zoom out. Environmental stress is one recurring theme. Overuse of forests, soil degradation, and the exhaustion of water sources have all contributed to civilizational decline. In those cases, the systems people depended on were pushed past their limits faster than they could recover. Resource depletion and climate shifts can feed into another pattern: conflict. As access to food, water, or arable land tightens, tensions climb. Wars break out. The infrastructure that supports everyday life becomes harder to maintain. Strain accumulates until the society can't absorb anymore. In the past, this kind of failure was regional. One culture could fall while others continued elsewhere. Today, our situation is very different. Our civilization is interconnected on a global scale. Energy grids, supply chains, financial systems, and digital networks link distant continents into a single, tightly coupled system. That global integration has undeniable advantages. But it also means that a failure in one place can cascade worldwide. A breakdown in food exports from one region can contribute to shortages on another continent. A disruption in fuel supply can ripple through transportation, healthcare, and communication. Shocks no longer stay local. On top of that, our technologies now reach into domains that previous civilizations never touched. We've split the atom, engineered microbes, built sprawling chemical industries, and woven digital networks into almost every aspect of our lives. These capabilities give us tools to mitigate some risks like tracking diseases or modeling climate, but they also create new species-level vulnerabilities. Nuclear weapons are the most obvious example. For the first time in our planet's history, one species holds the power to trigger destruction on a global scale in a matter of hours. The potential for runaway climate change, mass biodiversity loss, or large-scale ecosystem collapse represents a slower but equally serious kind of self-inflicted damage. Technological accidents add another layer. The more complex our systems become, the harder they are for any one person to fully understand. Power grids, data centers, industrial supply chains, biolabs, each relies on long chains of finely tuned interactions. A failure at one point can produce consequences far beyond what was anticipated. Pandemics illustrate how these vulnerabilities and connections intertwine. Dense populations, rapid travel, and trade can help diseases spread quickly across the globe. Our medical advances give us better tools to fight them, but those tools depend on functioning infrastructure. When that infrastructure is stressed, the line between a contained outbreak and a civilization-shaking event can be thin. Economic systems can also act as amplifiers. Societies built on perpetual growth can find themselves shaken by downturns, supply interruptions, or crises of confidence. When trust erodes, between citizens and institutions, or between nations, the coordination needed to respond to threats becomes harder to achieve. A collapse becomes planetary in scope when it doesn't just topple political structures or economies, but pushes the biosphere itself out of the range where advanced life can easily recover. A civilization might fall and be replaced by another, if the underlying ecological support systems remain intact. But if those systems are too damaged, if soils are exhausted, forests are destroyed, oceans are acidified, climates are wildly shifted, the world may no longer be able to host a similar civilization again. At that point, the planet moves closer to the graveyard. It may still have life, but not the kind of complexity it once did. From a wider perspective, each civilization is an experiment in how intelligence organizes itself. The experiment is always being run against the backdrop of a finite world with finite resilience. Growth, consumption, and technological innovation have to be balanced against long-term stability. When that balance fails, collapse becomes more likely. If intelligent life exists elsewhere, it may face similar pressures. Limited resources, environmental feedbacks, technological risks, social tensions. Civilizations that don't manage those forces well might disappear, leaving behind a planet that looks geologically ordinary, but carries subtle scars. A thin layer of unusual elements in the rock, a spike in atmospheric pollutants long since faded, a brief, sharp pulse in radio emissions that stopped ages ago. From far away, such a world might look indistinguishable from a purely failed planet that never hosted a civilization at all. The difference between never had and lost could be buried in chemistry and strata, not in obvious ruins. In the context of the graveyard of worlds, this possibility ties back into the Great Filter. If many civilizations self-destruct, then one of the hardest steps in the cosmic journey might not be the origin of life or the evolution of intelligence, but the leap from raw power to sustainable restraint. And while we can't yet know how other worlds have fared, we can see very clearly that we're in that phase right now. From here, though, we have to widen our gaze again. Even if a civilization navigates its own risks with grace, even if it manages its atmosphere and resources wisely, there's a larger clock ticking. Every planet lives in the shadow of its star and stars change. No matter how carefully a world tends itself, the light that sustains it will eventually shift, then fail. That's the backdrop all civilizations live against, the slow, relentless evolution of the star that made them possible. If Earth's story teaches us anything, it's that survival has always been a mixture of resilience and near misses. Our planet's history isn't a smooth climb from chaos to comfort. It's a jagged path, full of events that could easily have gone another way. Some of those brushes with disaster happened long before humans appeared, when life consisted only of microbes and simple cells. Billions of years ago, our sun shone dimmer than it does now, so dim that, by straightforward physics, Earth's surface should have been frozen solid. But the geological record tells us liquid water existed. This tension is known as the faint young sun paradox. The best explanations involve a combination of factors: higher levels of greenhouse gases in the early atmosphere, more volcanic outgassing, different continental layouts, possibly a different mix of clouds. However the details fall out, one point is clear. If Earth hadn't captured enough heat back then, our oceans might have frozen deeply and stayed that way. Life either wouldn't have started or would have been confined to a few limited refuges. Later, during the early days of the solar system, our planet endured heavy bombardment from asteroids and comets. Impacts powerful enough to vaporize oceans and strip atmosphere were more common. One such collision, early on, likely tore a chunk of Earth's outer layers away and gave birth to our moon. Had that event happened at a different time after life had already become established, it might have been sterilizing. Even after that chaotic era, dangerous impacts didn't simply stop. The asteroid that struck near today's Yucatan Peninsula 66 million years ago unleashed energy beyond any weapon we can currently build. It triggered fires, tsunamis, and a global dust veil that darkened the sky. Around 3/4 of all species died, but not everything died. Some lineages survived, adapted, and diversified. If that rock had been larger or hit a different region, the outcome could have been more final. The fact that complex life rebounded at all was another lucky break. Volcanism has also come close to unmaking Earth's biosphere. Around 252 million years ago, massive eruptions in what is now Siberia flooded huge regions with lava and spewed vast quantities of greenhouse gases into the atmosphere. The resulting climate disruption, ocean acidification, and loss of oxygen in the seas triggered the Great Dying, the worst mass extinction we know of. Roughly 90% of marine species and 70% of land vertebrate species vanished. Earth did eventually recover. New ecosystems emerged. But we can imagine a slightly different scenario: more sustained eruptions, higher gas outputs, or weaker negative feedbacks. In that timeline, the climate might have tipped into a state from which it never returned, perhaps resembling Venus more than Earth. Then there were the Snowball Earth episodes, hundreds of millions of years ago, when ice sheets may have reached all the way to the equator. If the planet truly froze over that extensively, only a few pocket subglacial lakes, hydrothermal vents, thin equatorial melt zones would have remained habitable. Life clung on in those niches. When volcanic CO2 built up enough to warm the planet, the ice retreated and new evolutionary bursts followed. But again, the outcome could have been different. If the ice had been thicker, the volcanic outgassing weaker, or the sun slightly dimmer, Earth might have stayed frozen for far longer. Photosynthesis could have collapsed, oxygen levels might have fallen, and complex life might never have had its chance. We can add quieter, but equally crucial, near misses. The continued operation of Earth's magnetic field, for instance. Generated by motions in our liquid outer core, it has shielded us from the solar wind for billions of years. Mars, by contrast, lost its global field early, and with it much of its atmosphere. Our field has flipped polarity many times and weakened during reversals, but it's never disappeared altogether during the age of life. If it had, perhaps our atmosphere would have eroded significantly, leaving us with a very different world. Even biology itself has nearly undone its own foundations. The Great Oxidation Event, more than 2 billion years ago, was driven by microbes that learned to use sunlight to split water and release oxygen. That oxygen built up in the atmosphere and oceans, toxic to many existing organisms at the time. It triggered a mass extinction. Only lineages that could tolerate or exploit oxygen survived to shape the future. From the standpoint of those earlier, oxygen-sensitive life forms, the emergence of oxygenic photosynthesis would have looked like an existential catastrophe. For us, it was a precondition. Throughout all of this, narrow escapes continued into the more recent past. The Toba supereruption about 74,000 years ago may have cooled the climate and reduced human populations dramatically. Some genetic studies suggest we went through a bottleneck, with relatively few ancestors surviving. Ice Age swings forced migrations and adaptations that might easily have failed. The point isn't that Earth has been constantly on the brink of total annihilation. It's that, again and again, conditions lined up such that we stayed just inside the range required for life to continue evolving toward greater complexity. A slightly different asteroid trajectory, a few more centuries of volcanic activity, a bit less greenhouse gas in the early atmosphere. Small differences could have undone whole chapters of our story. From the vantage point of the graveyard of worlds, this pattern of near misses is probably uncommon. Many planets likely faced similar challenges and didn't make it through. Some may have been hit one too many times. Others may have frozen or baked past the point of recovery. For every world like Earth that threads the needle repeatedly, there may be many more that don't. For us, these close calls carry a clear message. The stability we currently enjoy is not something we can take for granted. It's something that has been earned over and over by a combination of planetary feedbacks and plain luck. We can't control supervolcanoes, asteroid orbits, or stellar evolution. Not yet. But we can recognize that our position is precarious, and that some risks we now face are of our own making. To understand how rare it is to keep surviving these tests, we need to look again at the worlds that didn't get the same reprieves, the ones that fell off the ridge and never climbed back. Because in the patterns of their failures, we might find hints of how to extend our own improbable winning streak and avoid becoming just another quiet name in the universe's long, expanding graveyard. If we try to trace Earth's survival from its birth to this moment, the path we see isn't a smooth curve or a neat, predictable arc. It's jagged and branching, full of turns that could easily have led somewhere else. That's the footprint of chance and chaos, two forces that sit quietly behind every planetary story. When we at Echoes of the Forgotten Earth talk about chance here, we mean all the one-off, contingent events, the exact timing of a collision, the particular composition of a forming core, the angle at which an asteroid happens to strike. Chaos, in the mathematical sense, is different. It's not about isolated accidents, but about systems where tiny shifts in initial conditions can grow into huge differences over time. Both are woven through the history of worlds. Chance is easier for us to grasp. It's the random side of things, whether a young planet gets struck by a Mars-sized body that forms a stabilizing moon, or by something slightly larger that shatters it completely. Whether a rogue planet passes near enough to perturb orbits in a system, or misses by a cosmic hair. Whether a star forms with just enough iron and radioactive elements in a planet to be for that world to keep a molten core and a magnetic field. Each of those rolls of the dice shifts the eventual outcome of that world story. Chaos is subtler, but just as important. Planetary orbits, for example, are influenced by the gravity of every other object in the system. Over millions and billions of years, those countless small tugs can send orbits drifting. A world that starts comfortably in its star's habitable zone might slowly move inward or outward. Even slight changes in orbital shape can alter seasons, climates, and long-term stability. Climate systems themselves are classic examples of chaotic behavior. A tiny change in greenhouse gas concentration, a small shift in ocean circulation, a minor variation in solar output, each may seem insignificant alone. But over time, feedback loops can amplify those effects, tipping the entire system into a new state. Ice sheets grow or melt, deserts spread or retreat, rainfall patterns rearrange. On Earth, chance and chaos have been entwined from the beginning. The asteroid that ended the dinosaurs' era could have missed entirely if its timing were off by less than an hour. The Toba eruption might have coincided with a different climate phase and been much more or much less devastating. The early greenhouse that solved the faint young sun paradox might have failed if volcanic activity or atmospheric chemistry had been just a little different. In each case, the difference between we're here and we're not could come down to parameters so small we can barely measure them. Other planets in our solar system bear the marks of different rolls of the cosmic dice. Mars, with its lower mass, cooled faster, lost its dynamo, and watched its atmosphere fade away. Was that inevitable, given its size, or did it hinge on early collisions and interior composition that could have gone another way? Venus, perhaps very similar to Earth at first, may have slid into runaway warming because of slightly higher solar input, a different rotation pattern, or differences in early volcanism. In both cases, the divergence from Earth might have begun with tiny mismatches, but in chaotic systems, those mismatches grow. Billions of years later, the outcomes are drastically different. One world bearing oceans and forests, two neighboring worlds bearing deserts and infernos. This is why the simple diagram of a habitable zone, a green band around a star, is such an oversimplification. Being the right average distance is not enough. A planet can sit squarely in that band and still be uninhabitable if its particular cascade of chance events and chaotic feedbacks sends it in the wrong direction. The reverse is also possible. A world slightly outside the classic habitable zone might still maintain liquid water and a stable climate with the right combination of atmospheric composition, internal heating, and orbital characteristics. What matters isn't only where a planet starts, but what path it takes afterward. When scientists simulate planetary systems on computers, they often rerun the same starting conditions in slightly different ways, moving a planet's initial position by a tiny amount, or shifting a mass by a barely noticeable fraction. The resulting systems can look wildly different after enough time passes. In some runs, planets collide. In others, orbits stay stable. In some, habitable zones are filled with promising worlds. In others, everything ends up too hot or too cold. The real universe is doing its own version of these simulations all the time, with no resets. For life, this means that long-term stability is never entirely guaranteed, even on worlds that begin with great promise. On Earth, life has adapted to changing conditions again and again, finding new niches, evolving new strategies, rebounding after mass extinctions. But there are thresholds beyond which no amount of adaptation helps. A runaway greenhouse, a fully frozen ocean, a stripped atmosphere. Once a planet crosses those lines, the playing field itself is gone. From the vantage point of the planetary graveyard, chance and chaos are the invisible authors. They shape how many worlds ever get a chance at life, how many lose that chance before life appears, and how many lose it after life has already taken hold. They make it vanishingly unlikely that two planets, even if they start out almost identical, will remain similar after billions of years. This unpredictability complicates our search for life in a very practical way. We can find exoplanets in their stars' habitable zones and measure their sizes and orbits. We can even, in some cases, begin to sniff their atmospheres for certain gases. But those snapshots tell us very little about their full histories. A planet might look perfect from a distance. Right orbit, right size, apparently friendly air. Yet it could be in the middle of a slow collapse that won't be obvious for 1,000,000 years, or it could be coasting on the dying echo of a once vibrant biosphere that has already mostly vanished. The signs of that loss might be as subtle as a slight imbalance in atmospheric chemistry, or as hidden as fossil layers buried under kilometers of rock. There's another side to this coin. The same chance events and chaotic shifts that can end life can also open new doors for it. The impact that killed the non-avian dinosaurs cleared ecological space for mammals and eventually used to flourish. Shifts in climate have repeatedly forced organisms to adapt, diversify, and colonize new environments. Even extinctions can, in their aftermath, fuel bursts of innovation. Destruction and opportunity are intertwined. The question is whether the balance between them favors long-term complexity or resets the system too deeply, too often. What all of this means is that no world, not even one as apparently stable as Earth, can ever be fully insulated from randomness. We can model, prepare, and reduce certain risks, but we can't remove chaos from the equation. The best we can do is increase our resilience and our ability to adapt when the unexpected happens. On human scales, that means planning for a future that won't look exactly like the past. Changing climates, shifting coastlines, new combinations of natural and self-inflicted stresses. On cosmic scales, it means accepting that longevity is rare. Most planets will never enjoy billions of years in a stable, life-friendly state, not because physics is against life, but because the margin for error is small. From here, we can turn to a different kind of question. Given all this uncertainty, how do we actually look for living worlds out there? How do we distinguish a planet that's thriving from one that's coasting on the last remnants of its former habitability, or from one that lost its chance long ago? To do that, we have to think about traces, the signatures life leaves behind in air, rock, and light. And we have to be ready for the possibility that some of the most interesting worlds we find will not be alive now, but will carry echoes of a life they once hosted. Before we get there, though, it helps to remember that even worlds that fail don't simply drop out of the universe's story. They keep participating in a larger cycle one in which nothing, not even a dead planet, is ever truly wasted. The elements of worlds are always on the move. Stars form, shine, and die. In their death throes, some explode as supernovae, flinging heavy elements iron, nickel, carbon, oxygen into surrounding space. Others shed their outer layers more gently. Over time, this material accumulates in giant clouds. Gravity pulls those clouds together again, and new stars and planets are born from the ashes of the old. Earth is one of those second or third generation worlds. The iron in our core, the silicon in our crust, the carbon in our cells. They were all forged in earlier stars and recycled through earlier systems. We are living on and made of stellar debris. Planets themselves also participate in recycling. On Earth, plate tectonics constantly remakes the surface. Oceanic crust dives into the mantle and melts. New crust erupts at mid-ocean ridges. Mountains rise and are ground down by wind and water into sediment, which in turn can be compressed into new rock. Volcanic eruptions bring material from deep below to the surface, where it enters the cycles of weathering and life. The atmosphere is part of this loop as well. Gases enter it from volcanoes, from the deep earth, from the oceans, and from living organisms. They leave it through chemical reactions, burial in sediments, and escape to space. The carbon cycle in particular helps regulate climate over long spans of time, removing carbon dioxide when things get too warm and returning it when things get too cold, though only within certain limits. Life itself is a recycling engine. Plants and microbes take in carbon dioxide and nutrients, build organic matter, and release byproducts. Animals eat that matter, process it, and return different compounds to the air, water, and soil. Decomposers break down dead organisms, freeing their elements for another round. Our bodies are temporary arrangements of atoms that have been part of countless other forms before us. Destruction is just another phase of this process. Asteroid impacts vaporize rock and thrust dust into the sky. Over time, that dust settles and becomes part of new sediments. Supervolcanic eruptions bury landscapes, but the rocks and minerals they produce are later weathered into fertile soils. Even the most violent events are ways of redistributing material. On larger scales, planets can be broken apart entirely by collisions, tidal forces, or the violent expansion of a dying star. Their remains can form debris, disks, rings, or new generations of smaller bodies. Some fragments may eventually be incorporated into new planets. Meteorites we find on Earth sometimes carry traces of other bodies, like Mars. In principle, a chunk of a failed world can end up as part of a successful one. From the point of view of the universe, then, a failed planet is not an endpoint. It's a stage. Its materials continue to move, react, and reassemble. For civilizations, this has a poignant twist. The metals we mine to build our machines, the phosphorus in our DNA, the oxygen we breathe, they've all been through countless cycles before. Long after we're gone, the artifacts we leave behind will themselves erode, melt, or subduct, joining the planet's deeper layers. Perhaps in some far future, those atoms will rise to the surface again, in another context entirely. The graveyard of planets, in that light, is not a static field of tombstones. It's more like a compost heap on a cosmic scale. Worlds that lost their habitability contribute their matter and energy to whatever comes next. A planet's story as a living world may end, but the story of its material does not. This doesn't lessen the tragedy of loss for any creatures that lived there, but it does remind us that the universe is always, relentlessly, making use of what's left. For us, understanding this recycling matters for practical reasons. When we search for life elsewhere, we're not looking for exotic elements or substances unknown to physics. We're looking for recognizable patterns made out of very familiar atoms, carbon, oxygen, hydrogen, nitrogen arranged in improbable, energy-consuming ways. Those atoms are everywhere because dead stars and dead planets have been scattering them across space for billions of years. Recycling also influences how we might detect past life. Even if a biosphere is gone, its influence can persist in altered rock layers, unusual isotope ratios, or leftover atmospheric gases. Those traces can tell us that life once existed, even if it doesn't anymore. In that sense, dead worlds can still speak, if we know how to listen. From here, the story naturally circles back to the graveyard itself, not just as a metaphor, but as a real, expanding population of planets and moons, whose histories, if we can read them, may be our best guide to understanding how rare our own situation is, and how we might protect it. Because in the end, the question of failed worlds isn't only about what happens out there. It's about what we decide to do here, on the one world we can still influence. When we talk about the graveyard of worlds, it's tempting to picture a silent gallery. Cold planets, empty moons, dark spheres circling their stars in permanent quiet. But that quiet is deceptive. These worlds are not blank. They are archives. Every impact crater, every layered rock, every trapped pocket of ancient air is a record. Not a complete one, not a neatly written history, but a set of fragmentary pages from stories that span billions of years. If we learn how to read those pages, they can show us patterns in planetary life and death. And those patterns, in turn, can tell us where Earth might be headed. One of the first lessons is that habitability is not a fixed state. It's a moving target. Mars, with its old riverbeds and minerals that formed in water, shows us a planet that seems to have begun warm and wet, but now stands cold and arid. Venus, with its crushing, superheated atmosphere, likely spent time in a milder phase before tumbling into runaway greenhouse conditions. Neither world is frozen in the state it started in. Each evolved in ways that pushed it away from comfort, not toward it. That alone should make us cautious when we look at any planet, even Earth, and label it simply habitable. The label only applies to a slice of time. It says nothing about what came before or what will come next. A second lesson from the graveyard is that mass extinction isn't rare. On Earth, we highlight the Big Five extinction events, those times when a large fraction of all species vanished in geologically brief intervals. But the fossil record is full of smaller crashes as well, triggered by shifting sea levels, regional volcanism, changing climates, or biological innovations. If this is true on a planet as apparently fortunate as Earth, then it's likely that many worlds experience repeated die-offs. Some recover, some don't. A biosphere might be robust enough to bounce back multiple times, or fragile enough that one big disruption ends its complex life permanently. A third lesson is that planetary catastrophes can be both sudden and slow. Some are obvious: an asteroid impact, a supervolcano eruption, a nearby gamma-ray burst. Others creep up like a tide. The gradual brightening of a star nudges temperatures higher. A planet's interior cools, weakening its magnetic field. Volcanoes or weathering slowly alter atmospheric composition. Life, reacting to these changes, may alter its environment further, for better or worse. From the outside, it can be hard to tell which of these paths a planet is on. A world might appear perfectly fine for a long time and still be in the middle of a long slide. By the time the final tipping point is passed, there might be no dramatic marker, just a slow loss of diversity, a quiet thinning of ecosystems, an atmosphere drifting out of balance. The dead worlds also show us the limits of adaptation. We like to say that life is tenacious, and it is. On Earth, organisms have colonized deep rocks, boiling vents, polar ice, and acidic pools. But there are boundaries they cannot cross. Take away too much atmosphere, and radiation and vacuum win. Raise temperatures high enough and proteins and DNA fall apart. Freeze oceans solid, and energy and nutrients become scarce. Mars and Venus help define those boundaries. If life ever began on their surfaces, it could not follow the worlds into their current extremes. Somewhere along the way, conditions would have moved beyond even biology's elastic range. A fifth lesson is about timing. Survival isn't just about where a planet is or what it's made of. It's about when things happen. If Mars had kept its magnetic field a little longer, maybe its atmosphere would have lasted long enough for complex life to appear. If the most intense volcanic pulses on Earth had happened at slightly different intervals, they might have coincided with other stresses in ways that pushed our biosphere past recovery. If a world's good years are too brief, evolution may not have time to build the kinds of complexity we associate with forests, animals, or civilizations. This connects to perhaps the hardest lesson. Intelligence by itself doesn't guarantee safety. If other civilizations have ever flourished on other planets, some of them probably understood their own vulnerability. They may have detected their world's changing climate, mapped their own history of disasters, and developed technologies to mitigate risks. And yet, if the skies around us are any sign, None of them has filled the galaxy with unmistakable beacons or obvious artifacts. That doesn't prove they failed, but it suggests that successfully navigating the transition from technological adolescence to long-term stability is not easy. The graveyard also reminds us that no planet is fully in control of its own fate. Every world is linked to its star, its neighboring planets, and its galactic environment. A gas giant shifting its orbit can destabilize inner worlds. A star passing unusually close can perturb comet clouds. A supernova in the wrong region of the galaxy can bathe dozens of planets in radiation at once. Even a perfectly managed planet, if such a thing is possible, still lives under forces it cannot command. Above all, dead worlds ask us to be humble. It's tempting to tell Earth's story as if our emergence was inevitable, as if all the chaotic twists and near misses had to land this way. The graveyard tells us otherwise. It shows us many planets that might have looked promising at one time and are now empty. It frames us as the exception, not the rule. From a scientific perspective, that makes these worlds invaluable. Mars and Venus are laboratories where we can test our understanding of climate, geology, and atmospheric evolution. The icy moons let us study hidden oceans and strange chemistries. Exoplanets broaden the sample size, showing us worlds in orbits and configurations we'd never imagined before. By comparing these cases, we can start mapping the boundaries of long-term habitability. How much variation a world can tolerate, which feedbacks stabilize climates and which push them over edges, how internal and external forces interplay. This knowledge isn't academic. It feeds directly back into how we read the signs on Earth. If we know what a climate runaway looked like on Venus, we're better equipped to recognize the early hints of one here. If we understand how Mars lost its atmosphere, we can better gauge the importance of our own magnetic field and atmospheric processes. If we can identify exoplanets that appear to be past their habitable prime, we can refine our expectations for how long worlds like ours tend to last. But beyond the science, there's the perspective these dead worlds give us. They make it clear that life is precious because it is not guaranteed. They turn our everyday normal, the air, the water, the stable temperatures, into something extraordinary. We live at a time when Earth is still in its habitable window. Our biosphere is still rich. Our climate, while changing, is still within a range our species has adapted to. We have the tools to understand our planet's systems, to see some of the dangers coming, and to act in ways that other worlds never could. The graveyard doesn't tell us what to do with that knowledge. It only makes the stakes clearer. From here, we move outward again, away from individual graves and into the vast sweep of the galaxy, to ask a practical question. When we peer out into space with our instruments, what can we actually detect? How do we tell the difference between a living world, a dying world, and a dead one, when all we have to work with is faint light from unimaginably far away? To answer that, we have to think in terms of signals, gases in the air, colors of reflected light, heat signatures, maybe even artificial emissions. Some of those signals tell us that a world is thriving. Others, if we learn how to read them, might tell us that a planet's living days are behind it or running out. But before we can interpret those signs in the wider galaxy, we should recognize how fragile our own are, right here at home. It's easy, living inside Earth's bubble of breathable air and familiar weather, to feel like this is how the planet has always been and always will be. The atmosphere seems bottomless when we look up. The climate, though variable, has stayed within a band we consider normal for all of written history. Ecosystems still function, even as we alter them. Yet when we zoom out even a little, our present looks more like a narrow and delicate balance than a permanent state. The last 10,000 years, the span in which agriculture, cities, and civilizations arose, is a period of unusual climate stability. Before that, during the glacial-interglacial cycles of the Pleistocene, temperatures and ice covers swung more dramatically. After this, on long time scales, similar or even stranger changes are inevitable. Our current conditions are the product of a specific set of alignments, a particular orbital configuration, a certain mix of gases in the atmosphere, a specific arrangement of continents and ocean currents, a given level of volcanic activity, a sun that is stable on human timescales. None of these variables is locked in place. Earth's tilt wobbles and precesses, its orbit shifts subtly in shape, continental plates drift, the sun slowly brightens over hundreds of millions of years. Geological and biological processes alter the composition of the air. On top of this natural variability, we've now become a major agent of change. By burning fossil fuels, clearing forests, altering land surfaces, and releasing new chemicals into the environment, we've begun to push Earth's systems in directions and at speeds that don't match their recent history. Greenhouse gas concentrations have climbed sharply in just a couple of centuries, a blink by geological standards. The Earth system can accommodate some of this pressure. Feedback mechanisms can buffer certain changes, but they're not bottomless. Feedbacks can also amplify disruptions, as when melting ice reduces reflectivity and accelerates warming, or thawing permafrost releases more greenhouse gases. The fragility of our present isn't limited to physics and chemistry. Our food systems depend on relatively stable seasons, predictably timed rainfall, and fertile soil. Our water supplies rely on mountain snowpack, groundwater, and river flows that can be disrupted by drought, melting glaciers, or overuse. Our infrastructure from roads and buildings to power lines and data cables was designed for a certain range of conditions. As that range shifts, it becomes more stressed. Our globalized civilization adds another layer of sensitivity. Local shocks, crop failures, storms, power grid disruptions, regional conflicts can propagate through interconnected systems. A problem in one sector can quickly affect others. Food prices, migration patterns, political stability, and public health can all be influenced by changes in climate, biodiversity, or resource availability. Technology makes us both more resilient and more vulnerable. We can forecast storms, model pandemics, monitor ecosystems, and coordinate responses at scales that would have been impossible centuries ago. At the same time, we depend heavily on complex systems that can fail in unexpected ways. A single cyber attack, software bug, or infrastructure failure can have cascading effects far beyond its origin. On longer timescales, even if we manage our own impacts wisely, we still live under the slow evolution of the sun and the shifting patterns of Earth's orbit. Those changes won't transform our world overnight, but over tens or hundreds of millions of years, they will matter. The habitable zone moves. Our planet will eventually drift toward its inner edge, at some point far beyond any human planning horizon, but real nonetheless. Earth's surface will likely become too hot for complex life. All of this means that our current just right conditions are not a permanent feature. They are a temporary configuration, one that can be stretched, perhaps, kept within bounds for longer by wise choices, but not frozen forever. In the context of the graveyard of worlds, this makes our situation feel both precarious and urgent. We are living in a rare window where Earth is not only habitable, but richly habitable, and where we have both the awareness and the capacity to influence our future trajectory. The question is how we use that window. From here, we can shift our focus outward again, armed with what we've learned from dead neighbors and from our own fragile present, and ask, what do living and dying worlds look like from a distance? What clues should we be searching for in the light of faraway stars? And how can our understanding of Earth's story help us recognize a story like ours unfolding somewhere else or ending before it could? When people say, Earth is in the Goldilocks zone, they usually mean something simple. We orbit at just the right distance from the sun, not too hot, not too cold. For liquid water to exist on our surface, it's a comforting image, like a neat green band drawn around a star on a classroom poster. But the more we learn about actual planets, the more we see that just right is far messier than that picture suggests. Being the right distance from a star is only the first requirement. Staying just right is a much harder, ongoing challenge. And most worlds, if we're being honest, probably fail. The Goldilocks problem starts with the star itself. Stars are not constant light bulbs. They change over time. As they age, most slowly brighten. That means the habitable zone, the range where liquid water can exist on a planet's surface, moves outward. A planet that starts safely inside that zone may find itself creeping closer to the inner edge over hundreds of millions of years. Temperatures rise, oceans evaporate, greenhouse feedbacks intensify. The reverse can happen early on when stars are more volatile. Stronger flares and winds can strip atmospheres, especially from close-in planets, even if they initially formed in good positions. So the habitable zone isn't a fixed ring. It's a sliding window in both space and time. A planet has to land in that window and then somehow stay within it as the frame itself moves. The atmosphere is the next part of the puzzle. A bare rock at the right distance from a star will often be too cold its heat radiates away too efficiently. To moderate temperatures, a world needs some kind of insulating air with greenhouse gases to trap enough warmth. But there's a narrow sweet spot. Too thin an atmosphere and you end up with something like Mars. Cold, low pressure, with liquid water unstable on the surface. Too thick, with too many greenhouse gases, and you tilt toward Venus, an oven where any initial oceans boil away. Geology shapes this balance. A planet's interior heat drives volcanism, which pumps gases into the sky. Plate tectonics can help regulate carbon dioxide, burying carbon in rocks and releasing it again over long timescales. Without some mechanism like this, CO2 can either accumulate unchecked or be permanently locked away, pushing the climate toward extreme heat or deep freeze. Water adds its own layers of complexity. We often treat "has liquid water" as a yes-no checkbox. In reality, how much water a world has and where that water resides can matter just as much as whether it's liquid. An absolute water world, covered in a global ocean with no land, might sound ideal at first. But with no continents to weather and recycle nutrients, and no exposed rock to help regulate CO2, its climate and chemistry could evolve in very different ways. On the other hand, a nearly dry world might never develop the stable seas needed for life to begin at all. Even the distribution of water matters. Ice caps, glaciers, seasonal snow, and underground aquifers all play roles in a planet's energy balance and climate. A world locked in ice except for tiny equatorial melt zones might technically have liquid water, but only in thin strips, hardly a robust platform for complex biospheres. External influences layer on top of this. A large moon like ours can help stabilize a planet's axial tilt, keeping seasonal variations within a manageable range over long periods. Without such a stabilizer, tilt can wander chaotically, leading to erratic and extreme climate swings. Nearby giant planets can act as both protectors and threats. A Jupiter-like neighbor can gravitationally deflect many comets and asteroids that might otherwise slam into inner planets. But if its orbit is too eccentric or migrates significantly, it can destabilize smaller worlds, changing their orbits or even ejecting them from the system. The broader galactic environment plays a part too. Stars closer to the center of the galaxy may be more likely to experience nearby supernovae or intense radiation, which can strip atmospheres or damage biospheres. Stars in quieter, more isolated regions might offer safer long-term havens, but perhaps with fewer heavy elements to build rocky planets in the first place. Put all of this together, and the Goldilocks problem stops being a simple question of distance. It becomes a multi-dimensional balancing act, one that must hold steady within certain bounds for billions of years. Most planets will miss that balance. Some will start out in hostile conditions and never approach it. Others will brush against it briefly before drifting away. A few, like Earth so far, will manage to inhabit that narrow strip of just right for a surprisingly long time. From our perspective at Echoes of the Forgotten Earth, this has direct implications for how we search for other living worlds. When we flag an exoplanet as being in the habitable zone, that's really shorthand for worth a closer look. It does not mean this world is like Earth. Without detailed information about its atmosphere, its geologic activity, its water inventory, and its orbital history, we simply don't know. A planet could orbit in the perfect region and still be airless, or swaddled in a toxic, crushing atmosphere, or locked in synchronous rotation with one face scorched and the other frozen. It could be in the latter half of its habitable phase, already sliding toward a runaway greenhouse. It could be a world where life existed 1 billion years ago, but has long since vanished, leaving only chemical echoes. Time adds another twist. Life, especially complex life, takes time to evolve. If a planet's stint in the Goldilocks state is too short, there may not be enough time for anything beyond microbes to appear before conditions deteriorate. It's not just whether a planet ever passes through the right conditions, but how long it stays there, and how calm those conditions are. When we look back at Earth, we see how tight this window is. It took billions of years for complex multicellular life to arise, and only in the last tiny sliver of our history have beings appeared with the capacity to observe the cosmos and change the planet. That makes our current alignment feel even more improbable. We don't just exist on a planet in the habitable zone. We exist during the narrow band of that planet's habitable epoch when the climate is stable enough and the biosphere rich enough to support a technological civilization. In the graveyard of worlds, there are likely many planets that had their Goldilocks periods, but lost them, either too quickly or too catastrophically for complex life to gain a foothold. They might look deceptively calm now. Stable orbits, moderate temperatures, maybe even traces of familiar gases. Only up close, through the chemistry of their rocks or the structure of their sediments, would their stories of lost opportunity become clear. The Goldilocks problem, then, isn't just an academic curiosity. It's a reminder of how many ways a world can almost succeed, and how thin the margin really is between a living planet and a dead one. Which brings us back, inevitably, to ourselves. When we look at Earth with everything we've learned from Mars, Venus, the icy moons, and the theory of exoplanets in mind, we can't help but see how precarious our situation is. We have been extraordinarily lucky. We have robust but not indestructible feedback systems. We sit in a moving habitable zone. Our star is well behaved for now. We are not exempt from the same physics that filled the graveyard. We are simply at this moment on the right side of the line. The real question is whether we will stay there longer than most. From here, the path of thought leads naturally to choice. Knowing what we know now about fragile habitability, planetary failure, and the thinness of the Goldilocks line, what can we actually do? Can an intelligent species meaningfully tilt the odds in its favor, or are we still mostly passengers on a ship whose course was set long ago? To approach that, we first need to acknowledge something that's easy to ignore. We are both a remarkable exception and a candidate for the graveyard like every world that came before us. When we stand back and look at the graveyard of worlds, it's easy to draw one of two conclusions. The first is comforting. We must be special. We're clearly one of the rare planets that made it through a maze of hazards. The second is darker. We're only temporarily special. We've beaten the odds so far, but the same forces that emptied those other worlds are still out there, waiting for their chance. Both views contain pieces of the truth. On one hand, Earth clearly is an exception. So far, it's the only place we know where complex life has taken hold and developed the capacity to understand its own planetary context. That alone makes our world extraordinary. The specific conditions and coincidences that led to this moment would be very hard to reproduce exactly. On the other hand, every world in the graveyard was an exception at some point. Each once had its own moment of being the lucky one, a period when conditions were good enough, for long enough for something interesting to happen. Maybe that something was only chemistry. Maybe it was microbial life. Maybe it was forests and oceans. In a few cases, maybe it was civilizations. The graveyard is full of former exceptions. The difference between a living exception and a dead one isn't just in their starting points. It's in what happens afterward. It's in how long they manage to remain balanced on that narrow ridge of habitability, and whether anything on those worlds can see the cliff edges coming. We do have one advantage many planets probably never had: awareness. We can see, at least in outline, the kinds of threats that could end our own habitable era prematurely. We can measure greenhouse gases, watch glaciers retreat, track near-Earth objects, monitor solar activity, and study the geological and biological feedbacks that stabilize or destabilize our climate. We can act on that knowledge or choose not to. That awareness is not a magic shield. It doesn't protect us from everything. But it is a tool that no other species on Earth has had, and that many worlds in the graveyard likely never developed. If we want to remain an exception for longer than the average world, we'll have to use that tool wisely. That means, among other things, accepting that the conditions we enjoy are not guaranteed, recognizing that our atmosphere can be altered beyond what the biosphere can easily handle, understanding that mass extinctions, once triggered, unravel complex ecosystems in ways that are hard to reverse, acknowledging that our technology can be both a lifeline and a weapon. It also means learning from the dead worlds around us. Mars teaches us about atmospheric loss and the importance of a magnetic field. Venus shows us what unchecked greenhouse warming can do. The icy moons remind us that life can hide in unexpected places, and that surface appearances can be deceiving when we judge a world's potential or fate. Taken together, they sketch the outline of what failure looks like, not as punishment or destiny, but as a consequence of physics, chemistry, and sometimes biology itself. From here, our exploration turns to the marks we ourselves are leaving. Because one day, far in the future, someone or something may look back at Earth the way we now look at Mars and Venus. What will they see? A world that stayed in the habitable band longer than expected? Or another gravestone added to the long, quiet field? The answer will be written partly in rock and air, and partly in the choices we make now. When we picture the graveyard of worlds, it's easy to imagine it as a final resting place, a catalog of endings, each planet's story closed and filed away. But if we zoom out to the scale of cosmic time, failure is rarely an absolute end. A world that loses its habitability doesn't vanish. It becomes part of what the universe does next. Its gravity still shapes orbits. Its rocks still weather. Its atoms still move from one configuration to another, becoming ingredients for whatever follows. Think about collisions. When a large asteroid smashes into a planet, the immediate effects may be devastating. Shockwaves, firestorms, atmospheric upheaval. Yet that same impact can eject rock and ice into space. Some of that material may wander for eons before landing somewhere else. We've found meteorites on Earth that we know came from Mars. In principle, rock fragments from a failed or failing world could seed another with complex molecules, or even, in a speculative scenario, hardy microbes. That's one way a dead or dying planet might still participate in life's spread. Worlds can also influence one another without touching. A massive planet, even after losing its own surface habitability, can continue to shepherd comets and asteroids, altering the impact rates on neighboring worlds. A reflective, cloud-wrapped planet might change the light environment for its moons. A giant that migrates inward can push other planets into new orbits, some of which might move from frozen zones into warmer regions. In these ways, a failed world can inadvertently set the stage for another success. Some failed or marginally habitable planets may remain useful for life or civilization even after losing Earth-like conditions. A frozen planet far from its star can still have a subsurface ocean warmed by radioactive decay or tidal flexing, something like a supersized version of Europa. From orbit, such a world might look dead, airless, lightless, sealed in ice. Inside, it could host robust ecosystems. Even if no life exists there, such a planet could be valuable to any spacefaring civilization that comes later. It might offer water, minerals, and a deep gravitational well to work with resources for expanding into space. There's also the possibility of revival. While we often think of planetary habitability as a one-way trajectory, from friendly to hostile, some conditions can, in principle, swing back. A world that froze over completely might slowly thaw if its star brightens, or if its orbit shifts inward. A planet that lost its atmosphere might rebuild a thinner but sufficient envelope through long-term volcanism and cometary impacts. These processes unfold over immense timescales, far beyond any human planning horizon. But from the universe's point of view, a billion years is just one turn of the wheel. A planet might spend an eon in a dead state and then, under the right circumstances, drift into a new window of possibility. Beyond natural cycles, there's a more speculative but meaningful avenue: deliberate intervention. If a civilization becomes advanced enough, it might attempt to restore or create habitability on previously failed worlds. This is the idea behind terraforming engineering a planet's climate and environment to support life, possibly including one's own species. That could mean thickening an atmosphere, adding greenhouse gases to warm a frozen planet, or building vast shade structures to cool a hot one. It could involve importing volatiles, redirecting comets, or kick-starting chemical cycles that have stalled. None of this is anywhere near our current capabilities on an interstellar scale, but none of it violates known physics. In the very long run, failed planets could become canvases for new experiments in habitability, not only by nature, but by intelligent life. Of course, that kind of intervention brings its own ethical and practical questions. Is it right to resurrect a world that may still harbor hidden life of its own? Can we predict the long-term stability of a human-made climate? Would we be reviving a planet, or simply building a temporary shell that will slide back into its old fate once our artificial supports fail? The graveyard doesn't answer those questions. It only gives us examples of where worlds tend to end up when left alone. Even without intervention, the remnants of a failed world can be deeply informative. A planet that once had oceans and a thick atmosphere may preserve layers of sediment, fossilized life, and chemical signatures buried in rock. For future explorers, human or otherwise, those signatures would be an archive of what the world used to be, a narrative etched in minerals and isotopes. In that sense, a dead planet can serve as both museum and warning, a preserved record of what can be gained and lost. And even after geological records are eventually subducted or eroded away, the atoms themselves keep going. They might be scattered into space by impacts or stellar winds, incorporated into new stars and planets, or locked in smaller bodies like asteroids. Over and over, the universe takes apart what exists and builds something new from the pieces. If we apply this perspective to Earth, our planet's eventual end looks different. One day, whether through natural evolution of the sun or through earlier events, Earth will no longer be able to support its current biosphere. The oceans will eventually boil or freeze. The atmosphere will change beyond what complex life can endure. But the planet's matter will continue its journey. Our rocks may become part of some distant system. The elements in our bones, in our buildings, in our satellites, may eventually belong to some future world's oceans or crust. Within the graveyard, then, there's no absolute stopping point. There are only transitions. This doesn't make the loss of a habitable world any less real for the beings that live there, but it reframes failure as part of a larger, ongoing cycle rather than an isolated tragedy. For Echoes of the Forgotten Earth, this perspective has a double edge. On one side, it offers a kind of comfort. In a deep sense, nothing of us is truly lost. We and our world are temporary configurations of ancient matter and energy, participating in cycles that began long before life and will continue long after. On the other side, it sharpens the urgency of the present. Our particular configuration, the one that includes breathable air, liquid oceans, forests, and thinking beings, is fleeting. It will be gone long before the atoms disperse. That is the part we can influence. That is the part we stand to lose or preserve, at least for a while. From here, it makes sense to step back one more time and look not just at individual worlds, but at the graveyard as a whole, as a phase in the natural life cycle of planets. Because when we see that bigger picture clearly, our own position in it comes into focus with a new clarity. When we pull the camera all the way back from continents to planets, from planetary systems to the galaxy, we start to see a simple pattern beneath all the complexity. Worlds are born, worlds change, worlds die. They condense from the raw material of stars, heat up, differentiate into core and mantle and crust, shed or gain atmospheres. Some stay geologically active for billions of years. Others cool and lock into stillness sooner. Throughout, they orbit evolving stars in evolving galactic neighborhoods. The graveyard of worlds, in that sense, isn't a separate place. It's the final and longest chapter of most planets' lives. For a while, sometimes a very long while. They host active atmospheres, liquid water, dynamic climates. A subset hosts life. A smaller subset hosts complex ecosystems. A smaller subset still may host civilizations. Eventually, all of them pass out of those states. The number of planets that are currently in their rich, habitable phase is almost certainly tiny compared to the number that have already left it. That doesn't make the living ones less remarkable. It makes them more so. Our own position, then, is doubly rare. We are on one of those relatively few living worlds, and we inhabit it during an era when conditions are kind enough for intelligence and technology to arise. We are here at a time when we can look out, imagine the graveyard, and still have a say in when and how our own world joins it. That realization is humbling, but it isn't paralyzing. If anything, it clarifies what matters. No matter what we do, Earth will not stay habitable forever. The sun will evolve. The climate will change beyond our control on long timescales. Absolute permanence is not on the table, but premature failure is. The graveyard is filled with planets that, from our perspective, ended early worlds that lost their habitable conditions long before their stars died, or long before life had explored its full potential. Some of those endings were likely beyond anyone's control. Others, if civilizations were involved, might not have been. We don't yet know which category we'll fall into. We only know that we have an unusual capacity to influence the outcome. We can reduce the stresses we place on Earth's life support systems or increase them. We can build flexible, resilient societies or brittle ones. We can invest in understanding our planet deeply or ignore the warnings it gives us until events force us to pay attention. We can approach the graveyard as an eventual distant chapter we're trying to delay, or we can blunder into it much sooner than necessary. In that sense, the graveyard of worlds is less a destination than a context. It reminds us that the baseline state of the universe is not teeming life, but the absence of it, and that maintaining life, especially complex life, requires constant work against that baseline. Our choice is whether we treat that work as essential or optional, whether we see ourselves as temporary passengers or as caretakers earning our extra time in the narrow band between too soon and too late. Whatever we decide, some distant mind, if any, are out there, may one day look back at the faint spectrum of our planet and try to reconstruct what happened here. They might see a long era of thriving ecosystems and a civilization that managed to stretch its world's habitability far beyond the average. Or they might see a brief, sharp spike of industrial activity followed by a rapid return to simpler states. We cannot control how that story will be read. But right now, with oceans still flowing and air still breathable, we are still writing it. For now, the graveyard of planets is a place we can imagine and study, not one we belong to. Our chapter is still in progress, and that, in itself, is a gift most worlds never get. If you've stayed with Echoes of the Forgotten Earth through this long journey from living seas to dead deserts, from frozen moons to runaway greenhouses, thank you for lending your attention to a question that doesn't fit into quick answers. The graveyard is vast, but for this brief moment in cosmic time, we are among the living. Our task, as we see it, is simple to say and hard to do. Keep it that way for as long as we can. If you've stayed with me through this entire journey, thank you for giving your time and attention to this fragile, astonishing place we call home. From the vantage point of Echoes of the Forgotten Earth, the graveyard of worlds isn't just a distant, abstract idea, it's the backdrop against which our entire existence is playing out. Across our galaxy and beyond, there are almost certainly planets that tried and failed to do what Earth has managed so far. Some never quite reached the conditions we enjoy now. Others had them and lost them. Some may have nurtured civilizations that stared up at their skies, built stories about their own futures, and then slipped quietly into that long silence we've been imagining. We don't know their names, we don't know their histories. All we have are hints: dry riverbeds on Mars, sulfurous clouds on Venus, frozen oceans under ice, distant exoplanets with suspiciously thin or thick atmospheres. Each one is a clue, a single letter in an alphabet we're only beginning to read. Yet even these faint traces are already changing how we see ourselves. We used to imagine Earth standing alone in a cosmos of sterile rock and fire. Now we know that planets are common. Habitable zones are common. The chemistry of life, carbon, water, energy appears again and again. What's rare is persistence, holding on to that delicate balance long enough for complexity to bloom and consciousness to arise. Earth is one of the few that has managed that, at least for now. That doesn't make us chosen. It makes us fortunate and responsible. We are, at this moment, a species living on a world that still works. The oceans still circulate. The air is still thick enough to breathe and thin enough not to crush us. The climate is changing, but not yet beyond our capacity to respond. We are surrounded by other worlds that show us what failure can look like, in every direction: frozen, scorched, stripped, entombed, or emptied. Those worlds aren't there to scare us. They're there to teach us. Mars tells us that small changes in size and heat can mean the difference between lakes and deserts. Venus tells us that a shift in greenhouse gases can flip a planet from tolerable to lethal. The icy moons hint that life may exist in places we once wrote off as impossible, and that its disappearance might leave almost no surface trace. The exoplanets we're just beginning to study remind us that the universe is experimenting with worlds on a scale we can barely imagine. Some of those experiments will succeed. Many will not. Against that backdrop, our questions become sharper. How seriously do we take the thinness of our own margin? How much do we value our time among the living? How far are we willing to go? Not just technologically, but politically, culturally, and ethically, to avoid joining the silent majority before we have to. There are no guarantees. Even with perfect wisdom, we could still be blindsided by events beyond our control. But there's a difference between being overtaken by the slow, inevitable drift of stars and being dragged into the graveyard early by our own short-sightedness. Every generation has, in some sense, faced the unknown. Ours is different mainly in this: we're the first to see the entire planet at once. We've watched Earth rise above the moon's horizon. We've seen our world as a pale dot suspended in a shaft of sunlight. We've recognized in that view how small we are and how much we have to lose. We're also the first generation to know, with any confidence, that there are thousands of other planets out there, and that most of them will never look like home. For now, this is the one place in the universe where we know life is not just possible, but flourishing. Someday, that may change. We may find microbial mats under the ice of Europa or Enceladus. We may detect unmistakable chemical fingerprints of biology in the air of a distant exoplanet. We may even encounter signs of a civilization that isn't ours, faint, delayed, perhaps already extinct. If and when that happens, the graveyard will feel less hypothetical. It will become a shared reference, a reminder that we and any others we discover are part of the same precarious pattern. Until then, we have this: one world, one fragile window of habitability, and the choice of how we act while it's open. We can treat Earth as a disposable stage set, assuming that something else or somewhere else will always be available when this place becomes difficult. Or we can treat it as what it is: an improbably stable refuge in a universe where stability is temporary and life is the rare exception rather than the rule. The graveyard of worlds will continue to grow, with or without us. New planets will cool. Old ones will fall silent. Stars will be born, flare, and fade. Matter will keep cycling through forms we'll never see. Our story, though, is still being written. We are not just witnesses to this era of Earth's life. We are participants with the power to accelerate its end, or to slow it, to soften it, to give our world more time as one of the few oases in a harsh and restless cosmos. Here, at Echoes of the Forgotten Earth, That is the thought we keep returning to. We are living on a world that has, against long odds, escaped the graveyard so far. We can't undo the physics that will eventually place it there, but we can decide whether it happens soon, in a burst of self-inflicted crisis, or late, after a long, rich extension of this rare, habitable chapter. Seen from that angle, every choice we make about energy, about ecosystems, about conflict, about cooperation is bigger than it looks. It's not just about comfort or prosperity or even justice in the short term. It's about how long Earth's name stays off that quiet cosmic list of lost worlds. For now, we are still breathing, still able to look up at a sky that protects us and a universe that, for all its indifference, has given us this extraordinary opportunity. The graveyard is patient. It can wait. The question is whether we can learn to deserve the time we've been given before our planet joins that long procession. If you've listened all the way to the end, thank you. Not for supporting a channel or a creator, but for allowing yourself to think slowly about something that doesn't fit neatly into a headline. If this way of exploring the universe speaks to you, unhurried, reflective, grounded in both science and a sense of wonder, consider staying with echoes of the forgotten Earth a little longer. There are many more stories to tell, of worlds that were, worlds that are, and worlds that might yet be. And as long as we're here, we can keep telling them from the side of the living.